it's just fantastic to see everybody here and so many people, friends, family members, and of course the graduating class of MIDS Summer 2020. My name's Steve Weber. For those who don't know me, I'm the Associate Dean and Head of School at iSchool Berkeley and professor at the iSchool. And for me, the MIDS program is really special because I was involved at the very start in trying to work with Anno Saxenian and others to conceptualize what this program would look like. And I have to say it succeeded beyond some of our wildest imagination, and it's fantastic for us, and I hope it's equally fantastic for everybody else. The capstone was originally thought of as kind of the culmination of all the work that students put in over the long period of time that they go through this program. And so we have a sense of just how much many months of study and work go into these projects. And we also know that many of our mid students are people who have full-time lives elsewhere, jobs, families, little kids, in the middle of a pandemic, to make it more interesting and more complicated. So I just want to thank everybody for that work and the dedication that goes with it. I can't actually even imagine some of the challenges people have had to put up with in the last 6 to 8 months, but you've powered through, and that's amazing. So tonight we're going to see a variety of projects and approaches to various needs and problems. There are a couple of projects I know that are related directly to different aspects of COVID. And one of the things that's always been unique and interesting and distinctive for me about the MIDS projects is the way they have this kind of end-to-end character. It's never just, here's the algorithm. It's always a solution to a problem thought from end to end. And that's what makes it both so exciting intellectually, but I think also just kind of underlines why the world needs these kinds of educational experiences and needs the graduates from these kinds of educational programs to go out and do the things they're going to do. So congratulations to everybody. I'm really excited to listen to the projects. Let me just quickly introduce 3 folks who have joined us tonight to judge the projects. We have Deval Bhatt, who is a product management professional, has had 10 years of experience in products analytics and marketing. He also is an alum of the program, which makes him even better. He graduated in 2016. Deval, thanks. You're an entrepreneur and co-creator of Squibbler, a writing software product, which I haven't seen, but I am going to test out later tonight. So I hope everybody else will do the same. Ruman Chowdhury is global lead for responsible AI at Accenture Applied Intelligence. Ruman's interested in how data can be used to understand and counter bias and ways to evaluate the impact of technology on humanity, which is of course what the iSchool is all about. And Ruman has contributed significant work on algorithmic ethics, fairness, and justice. So thank you, Ruman, for joining us here tonight. And finally, Sharon Lin. And I have to confess, Sharon was in the very first, if I got it right, the very first cohort of MIDS when I was teaching in the synchronous as well as the asynchronous. So that seems like 150,000 years ago, Sharon, but it wasn't that long ago, because I now know that you were class speaker for the very first graduating cohort in 2014. So that was a different time. Sharon is the director of creative analytics at Twitch, which I'm sure everybody knows. And before that, she was a data scientist at Okta, which is a cloud security and identity management company. And she continues as a mentor to our 5th-year MIDS students program, which is a really important extension of this program to the iSchool and to Berkeley as a whole. So just one last thanks and congratulations to everybody. I want to turn it over to Drew Pollan, who everyone knows as the academic director of the data science program at the iSchool. Drew's also going to be judging. I think Drew is also going to be the bad guy when it comes to timing, and he is a really bad guy when it comes to timing. So over to you, Drew, and thanks again, everybody.
Thank you, Steve. Yeah, I also want to congratulate all of the capstone students who are completing MIDS this term. Really well done. So tonight we have 8 teams presenting their projects. Each team is going to have 15 minutes to present, and then there's going to be a 5-minute question and answer period in which our judges will ask the team some questions. So yeah, our judges are going to be posing questions to the teams after their presentations, but if you in the audience have questions, please do post it in the question and answer tool, which is below in the bottom of the Zoom interface. And Teams, you can post your answers there as well. You can also use the chat to ask people questions and discuss things. But please do ensure that you have it set to all panelists and attendees. That way it'll ensure that everybody in the room can see your questions and your responses. So with that, let's get started. First up, we have a project titled WildTrack AI. So WildTrack AI team, please start whenever you're ready.
All right. Thank you. Can someone confirm that you can see my screen?
Yep.
A few rhinos and a few other animals. All right. All right, Mike, take it away.
All right. Good evening, everyone. On behalf of the WildTrack AI team, thanks for joining us. And we actually wanted to start off tonight with a brief message from the WildTrack founders, who we partnered with in the development of this capstone project, to provide some context on the idea behind WildTrack AI.
Hi, we are wildlife biologists and WildTrack co-founders. I'm Sky Alibi.
And I'm Zoe Jewell. Species are going extinct up to 10,000 times background rates. COVID-19 is a direct result of our reckless destruction of the natural world.
We do conservation from the ground up, protecting endangered species using footprints. This non-invasive model reduces disturbance to animals and the risk of disease transmission to humans. Our footprint identification technique, FIT, is accurate but time-consuming and requires expert knowledge.
Increasingly, we have more data than we can manage, and so that's why we approached our team at UC Berkeley with a very big ask.
Could AI help us facilitate data processing and analysis? As far as we know, no other AI team has done this with an object as cryptic as a footprint.
So as Zoe and Sky laid out for us, the problem that this project attempts to address is whether cutting-edge computer vision technology can be applied to improve the speed and accuracy of animal classification using footprint imagery. And by improving the monitoring of wildlife behavior in this way, we will be in a better position to protect endangered species, reduce biodiversity loss, and even reduce the risk of disease transmission to humans, which has become increasingly relevant in recent months. So to achieve this, we focused on two primary user personas and use cases. First, field researchers such as Baron Reinhardt, pictured here, who tracks rhinos in Namibia. Baron is responsible for field-based data capture, and he seeks confirmation on his species and individual predictions, as well as expert feedback from the WildTrack administrators on the images he's generating. And second, the WildTrack administrators themselves, who are in need of a centralized system to manage the images and their attributes, AI models, and also provide an interactive feedback mechanism to the field researchers. The following diagram depicts the basic sequence of our data flow, from data capture and processing to footprint detection and inference, and finally, expert feedback and user interface. This process integrates a wide variety of platforms and software, as we'll describe in detail, and is automated from start to finish. And now to demonstrate the first stage of this process, data capture, is one of WildTrack's field researchers.
First of all, quickly I introduce myself. I'm Berend Reinhardt, together with Friedrich, my brother. Take a series of pictures of this track. At Kusikos Wildlife Reserve, we are out here in the bush. We just tracked some rhino, and we took some photos to feed into the WildTrack AI webpage.
So the system which Baron has just demonstrated leverages a third-party open source data collection platform, which we integrated into our pipeline, and has helped us increase the number of images feeding the system by more than 50% in just the last 2 months. So picking up where Baron left off, we're going to go into a brief demonstration of the user aspect of the interface. So as a user, I come into this landing page where I can find some basic summary statistics on image generation, existing models and model performance on the latest images. I can also see the current leaderboard for field-based image generation, which helps motivate me to collect more images as a field researcher. From here, I can also drill down to specific footprint observations I've made in the field. I can compare my species predictions with those of the AI model, and also access image quality rankings and qualitative feedback from the WildTrack administrators. So from here, Jacques is going to give us a glimpse into the underlying AI models at the core of this work.
Thank you, Mike. As you can see on this overview, we build a total of 4 models to be used in combination to power our inference engine. So we have 1 footprint detection model. We have 2 models for species classification, VGG19 and YOLO v3. And then we have a model for individuals identification. We initially trained all the models on about 3,000 images. For the detection task, because in the future we wanted to move to the edge, we chose YOLO v3, which has the best inference time for the map score on the COCO challenge. We used the Keras implementation with the TensorFlow backend. For species classification, we explored different pre-trained models on ImageNet and selected VGG19 for our end-to-end pipeline for its accuracy and size. We had best results when allowing all layers to train, i.e. no frozen layers. We used ensemble modeling here by predicting with both VGG19 and YOLO v3. For individual identification, we started with the pre-trained species classification model weights, and for each species, trained on a triplet network architecture to produce 256-dimensional vector embeddings for each footprint, such that footprints of the same individual had vectors that were closer together in Euclidean space than footprints for different individuals. Once the system was deployed, we were able to monitor performance on new field images, since they are often labeled either by researchers in the field or by the WildTrack founders. We saw a big difference in the initial data set and the new field images, resulting in a drop in accuracy. As you can see on the left side, we have 3 examples of our training images. They were cropped to just a north-south orientation of a single footprint, always left hindfoot and of high quality. The images that we are receiving, however, as you can see those 4 examples on the right side, they may have multiple footprints, aren't always left hindfoot, have variable quality, and often have markers that the researchers use for analysis, like the rulers. In order to mitigate the gap, the main techniques we employed thus far with positive results are the addition of the YOLO model for detection and classification, and the use of image augmentation when training the VGG19 models for all tasks. We have also updated the system to store and utilize user-entered labels that can be used at inference to further improve the accuracy of the predictions. And finally, we have the ability for the system administrators to add new images to the training set for incremental retraining of the models. I will now pass it on to Jonathan for the administration use case.
Thanks, Jacques. As we worked with our initial set of users, we uncovered a much broader set of requirements that needed to be addressed in order to truly make this system the primary hub for their research and tracking going forward. In order to give you a glimpse of those capabilities, I'm going to wear the hat of the administrator, Zoe, and switch back to our administration site. I'm here in the Images tab, where I review recently uploaded images. In addition to enabling us to get feedback out to partners in the field, we found that the rating the quality of the images is critical to allow us to more accurately assess even the performance of our models. I see that the species prediction model seems to have done pretty well for this new batch of order images that have come in over the last few days, especially considering that some of them are of a lower quality. I can look at the images in detail to see how the footprint detection model is doing. In this case, I see that it has picked up some of the prints, but not others. And I do have the option here of adding this image that came into my training set so that the next time the model is trained or retrained, it incorporates these images as well. One of the things that we don't have enough of is enough images that have multiple footprints. And so the ability to add images to the training set on the fly has helped. Since this is a live system and I only play a conservation biologist on TV, I'm not going to save this, but I'm going to cancel out of here. Ongoing monitoring of model performance as new images come in has been key to our being able to start really mitigating that distribution gap that Jacques mentioned. As you can see, for species classification, almost all species have field performance on par with test performance, which is a huge improvement over the 30 to 40% drop in accuracy we saw when we first deployed the model. We did receive a batch of images over the last couple of weeks for lion and leopard specifically, where the model isn't performing too well, as you can see, for field images. Early analysis shows a sandy substrate for a number of these images, where the imprint isn't as pronounced. And this is different from the images we trained on. So as a next step, we're incorporating some of those images in our training set for further fine-tuning of the model. And we're also exploring additional augmentation and image filtering options. Our biggest learning really with this project was that the initial deployment of the models was just a start of the journey rather than its culmination. The real heavy lifting needed was to leave Wildtrak and their user community with a self-managed system that they could adapt to be resilient to variation in field data, in addition to being scalable to more data and more variety of data. This had us adding features like master list management for species and individuals, master list management for users, as well as providing a very active research community a channel for feedback. To give us an overview of the technical design choices we made to support system scalability and adaptability, I'm going to hand it back over to Dan.
Thank you, Jonathan. This image presents a view of our overall system architecture. Scalability and sustainability were front of mind in our design choices for the system. As Sky mentioned in his introduction, prior techniques, while accurate, are time-consuming and require expert knowledge. Think scalability. And as Zoe further elaborated, Wildtrak had more image data than they could manage. Think sustainability. We sought to engineer a system to meet those goals. Sustainability is featured in containerization of elements in our pipeline with payoffs. We knew there needed to be knowledge transfer from our team of 4 to the good folks at Wildtrak, but the need also developed to transfer our entire system. We were instrumental in authoring a grant proposal to successfully secure $10,000 of cloud credit on Microsoft's Azure system. In evaluating the success of this project, we focused on 5 key criteria. We succeeded in expanding use cases of this technology, providing species prediction, expanding the user base to non-expert trackers, and providing a feedback mechanism to users. And while we did not outperform Wildtrak's FIT technology in terms of accuracy, Wildtrak AI delivered comparable results and significantly reduced the amount of time to generate and deploy new predictive models when comparing Wildtrak AI training time to time spent preparing images for FIT algorithms. In terms of model tolerance, we were able to adapt the system to accept less than perfect images while still delivering accurate predictions. And finally, our system is built on a generalizable framework that can be easily adapted to applications in other spaces. As Mike stated earlier, our user personas include field researchers and administrators, but there is a third persona called the casual user, the citizen scientist, if you will. Complementing the success criteria for reducing the amount of time to generate and deploy new predictive models, we have had late-breaking noteworthy success embedding the YOLO V3 model on an edge device. Our edge device is an Android tablet, pictured here, producing spectacular results in most cases, particularly considering finding the footprint with the bounding box is the first step in the inference flow. We are excited about bringing AI to the edge. A big testament to the generalizability of this framework is that we all have plans to continue working with the technologies that we have developed. Key to note is the diversity of future projects, from domains such as agriculture to turtle shells, to trail detection on drones, to the analysis of other forms of cryptic ground evidence. And now we have a closing message from Wildtrak.
These analytics can revolutionize our understanding of how best to protect wildlife and humanity. So where do we go from here? The Berkeley team has delivered a solution to the #1 challenge of our times, in our opinion, protecting biodiversity.
This new Wildtrak AI tool will enable us to rapidly process data and deploy solutions to where they're most needed.
Moving forward, we want to bring in more data to develop more species and individual algorithms. You guys have already exceeded our wildest expectations. Thank you.
Thank you.
So thanks to the Berkeley group, thanks to Wildtrack, thanks to make this happen. Always glad to participate in projects like that here. Right here.
And that's a wrap. We're open for questions.
Excellent. Thanks. Judges, questions?
I guess I'll start. Well, first of all, thank you so much for the presentation. It's definitely a very inspirational project. I have a couple questions. So when you were talking about model selection, you guys mentioned about optimization on accuracy and size. Did you guys take into consideration on cost and speed in this case as well? Because you mentioned that later on you can add additional image back into, apologize for my dog. Have you guys talked about potentially when you add images back into the training set, how often would you guys expect to retrain your data set? So that's sort of my general question around just trade-off in this case.
Yep. Quite frankly, or quite honestly, initially, our focus was purely on, can we even use these ImageNet models, use transfer learning, and use them on footprints? Because as far as we saw using literature research, no one had ever done something like that. So we were primarily optimizing for accuracy and the ability of the model to do it in the first place. Some of the models didn't really work, and we were actually surprised that VGG did, because given it's an older generation model. But since then, what we focused on is also the ability to do incremental retraining with those models. So as data is coming in, I'd say right now we have probably a month's worth of evidence. So over the last month, we've retrained the model, at least once, if not twice a week. And the species classification model just takes an hour or two. The individual, because we have to train once for a specific model for each species, that takes longer. So, the entire sequence probably takes 48 hours.
Thank you.
No problem. Other questions from the judges?
I have a follow-on question on that one. Can you hear me okay?
Yep.
First of all, great Joe, awesome. Like the level of sophistication that I have seen over the course of years that has happened in this project, it's just amazing. Big props to all of you for getting it to this point. So one question I have is, what is your plan for acquiring and incentivizing your users so as to get more images? So, for example, Google Maps, where they send out, hey, this is your summary of things. Like, you have uploaded this image 5 years ago, you were here, and that puts me in that state where I want to contribute more. So what are some of your plans to get the users to contribute more to get more images and ultimately help biodiversity?
Sure, I'll channel Zoe and Sky and hit a couple points, and then others feel free to join in. So we started with, we're fortunate that we work with Wildtrack, who have a very engaged community of field researchers across the world. We have people from Namibia, from the Amazon, from Israel sending us images. And their motivation is primarily wanting to see feedback, and they're really invested in seeing this project succeed, because in some way, shape, or form, the success of this project helps them with their work, helps them with doing their analysis faster, et cetera, et cetera. And so that's really a virtuous cycle that we can take advantage of. And just in the month, I'd say 4 to 8 weeks that we've had the system live, you can see the momentum building. We started with a few images trickling in, and now, literally there's images coming in daily where, I have to log in every day to look at how the model is doing, et cetera. So that's been great. So that's one, and I think that forms the core critical mass of this project. The next piece, and Zoe and Sky are actively doing this, is they're cultivating relationships with tourism groups, ecotourism, et cetera, where they want to incorporate this notion, think of it as gamification of wildlife conservation, with maybe if a school is going on a field trip, they can go collect images and upload it to this site and maybe get a prize, right? So they're in a lot of conversations with organizations such as that across the globe to be able to drive campaigns, if you will, where there's immediate value to that organization, but the net result is it's over time behind the scenes building up a data asset for WildTrack.
Very cool. Thank you for sharing that.
So I'll hop in here. So again, I want to reiterate what the other two judges said. Really excellent project. I think, for me, what I love is, it's such an end-to-end complete tool. It's not just a model that you've built, it's also the platform, etc. And that is no insignificant amount of work to create a usable platform. Another thing I will say as a big plus is it's always important to me personally that, for people to solve problems that are useful for people who are not technical people. So I do want to applaud specifically the fact that you've built something that's useful to an animal tracker out in the wild who does not know or care about artificial intelligence or data science, except in that, whether or not it is useful to them. So I think if, these individuals are saying this is useful, this is helpful, that's really a massive win. So kudos to you for that. My question is actually on your third user persona of the citizen contributor. So that individual is notably different, right? So, here you may come into maybe malicious use, not even malicious like someone's trying to hack it, but, like people like to do dumb things, right? Like once you open things to the public, people do dumb things, right? How are you thinking about that user maybe differently than you would think about your typical user who is a wildlife conservation individual who is very invested in seeing this platform succeed versus the third group that you mentioned, which was something like, okay, folks on ecotourism, holiday, etc. What are the kinds of user considerations you're making, and what changes might you make to either your model or your platform or your usability to address that?
Dan, you want to take that so I don't monopolize?
Sure, that'd be great. So when we initially started the project, we did some interviews with people to kind of get an idea of how they would use the platform, use the tool, and things of that nature. And we came across the idea of needing to have a resource for managing incidents, and maybe a shepherd might have one predation is how it's described, might have a predation incident where endangered species might kill one of its flock. And in that case, that's kind of the prelude to the Android app, is having a tool that allows you to identify print, but not necessarily a tool to submit the print in the same way that we did with the EpiCollect. So we have multiple entry points in our pipeline to accommodate the different personas.
I think the key there is our view is the third persona, the citizen scientist, is the value for them is a byproduct of the interaction across the first two. So really getting data, getting the right footprints, fine-tuning the model, allows us to then create a pretty accurate app that we can deploy on the edge, where its primary use is for someone who's interested in knowing, all right, I see this print, what is it, what animal, and can I identify it, versus they're actually submitting into the main system. So we weren't thinking of it to the point where they were actually submitting data, but more using it for its utility to just help them identify what species they see.
Just as a final point on that, sorry, just as a final point on that, the issue of GPS came up a lot in our data collection and how we present the information. And that was a concern for a lot of the field researchers in terms of tracking endangered species and being kind of cautious about tagging GPS information. So at this point, we do have a certain amount of it and we're collecting it, but we purposely haven't presented it yet on the front end until we work out kind of that more secure and the security issues in relation to collecting that type of information.
Great, thank you.
Excellent. Thank you so much, WildTrack AI team.
Thank you.
Next up, we have COVID EXP team. Whenever you're ready.
All right, I'm just gonna share my screen. Can you all see my screen?
Yes.
All right, we're gonna get started. Thank you everyone for being here, the panelists, judges, everyone else who's here, everyone else who's tuning in as well. Appreciate your time. I'm Hirsch, along with Luca and Marcus. We focused on COVID-X, a pipeline for X-ray examination of COVID. And what our work really focused on was automatic labeling of X-ray scans in collaboration with health operators in India. So to give you a little bit of background, India was hit particularly hard by the pandemic. And at the start of when we started to look at this project, India only had 3% of the cases worldwide, with over 17% of the world's population. Since then, and this was, I think, from last week, Johns Hopkins just released that India now ranks 3rd globally in terms of the amount of people affected. So you can see in this about 12 to 14 week span, the amount of cases have skyrocketed. And what we see is that the healthcare system is under strenuous pressure. And we really saw an opportunity to introduce machine learning in order to assist the diagnosis of COVID-like symptoms. Now, I want to make it clear to say that it's not as if our algorithm and our kind of end product is going to be replacing a doctor to identify COVID. Rather, it would be used in connection with certain doctors and maybe prioritize images for them. And say they have 1,000 images, we can tell them which ones we think have COVID, and then they can go and do the analysis themselves. Also, to give you a little bit of background, we're focusing on the Gujarat region of India, which is circled on the map here, which has a population of 60 million people. Now, if I showed you these images and I asked you, hey, what are the different things going on in these images? Could you figure it out? Maybe, but it's actually a lot harder than it may seem. And this is actually reflected in where doctors are predicting now, right? They're predicting at about 80 to 82% on 6 different classes of different diseases and issues within your lungs. You can see what the normal image looks like. It's pretty easy to identify, but if you try to look between ARDS, which is kind of one of the worst things that can happen to your lungs, it's like late stage COVID or other issues, and TB, the images look extremely similar. It's really hard to visually tell a difference, right? And this is where we thought we could have an immediate impact. And so when we started looking at images and we saw a lot of images that were available to the public, and we ran it past our contacts within India, we saw a lot of them were actually mislabeled. And so a lot of the open sourced images we can't use to train our model on. So what we did was created a data acquisition pipeline where we got real images from real patients from India. And I'm happy to go into the structure of how we did so a little bit later if need be. But what we got was kind of this portal right here on the left-hand side, where all one had to do was upload a zip file of the images that they had, and we'd take care of the rest. And the reason we did this is because technical literacy is oftentimes a big issue within India and the doctors we were working with. So we wanted to make it as simple as possible for doctors to upload pre-labeled images so that we could actually train our model on. And what we came out with was about 1,050 normal images, about 450 atypical images, and atypical is where COVID-like symptoms would rest. About 128 typical, 305 other, about 100 TB, and 400 ARDS. And with that, I'm going to pass it off to Luca to talk a little bit more about our inference pipeline.
Thank you, Hirsch. We're showing our inference pipeline here. We opted for a 2-stage design, whereby first model performs a binary classification among normal versus any other condition. And the second model is tasked with predicting the actual condition among the 6 that Hirsch just introduced. There are 3 reasons why we chose a 2-stage approach. The first reason is mainly cultural. During the project, we learned that the concept of multiple stage testing is ingrained in medical practice. And as such, we thought that designing our solution around this concept would resonate better with the cultural background of the end users and hence possibly increase adoption. Secondly, a 2-stage approach, such as the one we're showing here, ensures that an image is labeled as anomalous only after 2 different model instances have classified it as such, thus increasing precision, which we believe is a desirable feature here. Thirdly, a two-stage approach allows more flexibility. We could, for example, add additional binary models on the first stage, thus increasing creating a model ensemble, whereby an image is labeled normal only if there is consensus across all ensemble members. This is a setup that we tested at some point during the project as an offline solution and which proved to boost recall, which is again a desirable feature. Next slide, please. As for the models, for the first stage, the binary classification, we tried out a varied range of architectures, as this matrix shows here. Looking at accuracy and AUC metrics on the validation set, we see that the highest performance is provided by MobileNet and DenseNet architectures, both scoring around 90% accuracy. We selected DenseNet in the end because this came pre-shipped with Clara, which is the environment we use for our pipeline, of which Marcus will show in a minute. And that saved us quite some time during the project. On the basis of the binary results, we went straight in for DenseNet also for the second stage modeling. And again, we see an overall accuracy of about 90%, which is considerably higher than the baseline characterizing trained radiologists that Hirsch mentioned previously. Next slide, please. So as I mentioned, DenseNet is the architecture that we ended up using for both stages. We train this architecture with transfer learning. What I really want to draw your attention on here is the resolution of the input image, which is specified in the first line here on the list to the right. As we can see, it is a 3 channels 256 by 256, which is considerably finer than the resolution of the inputs of the other architectures that we tried. So we presume such finer resolution could be one of the reasons of the overall, better performance of this architecture over the other ones we tried. Next slide, please. I should also mention that we equipped the first binary model with LIME. LIME stands for Locally Interpretable Model Agnostic Explanation, and is an interpretability engine that can be used to check whether a model behaves plausibly. In the context of image classification, LIME highlights the areas of the image that contribute the most to a given predicted class. So let's first take a look at this example from the LIME author's GitHub page. This is an image we sent to a classifier. The classifier predicts the image subject is a Bernese mountain dog, as indicated on the slide. Now, LIME takes the image and the model and computes the regions within the image which the model is most sensitive to when making the given prediction. In this example, we see the model is actually looking at the dog when making its prediction. LIME can thus be used to examine whether the model is looking at relevant artifacts within the image while making its prediction. Hence, its use in an interpretability context. Next slide. And this is one example application of LIME as written by our pipeline. What we see here is that the model looks at the upper lung regions, which are presumably relevant regions when examining X-rays for pulmonary conditions. And this kind of improves confidence in the model quality. And now we'll leave to Marcus to show you a live demo of our pipeline. Thank you.
Thanks, Luca. I'm going to share my screen. Please let me know when you can see it.
You can see it.
All right, great. Hi, everybody. Good evening. So what we see here is the inference and LIME engine interface that a typical radiologist in India would have. It uses the DICOM format, which is a medical metadata format. It basically it's portability of the medical data along with the image. The images themselves are about 5 megabytes large. So a large part of our effort was to help with upload and download latency by resizing the image as part of our pipeline. And I thought what we'd do is first start with a normal case, a normal chest X-ray exam. And as we can see here in this portal, the original image was submitted Friday, May the 1st. And then it was submitted to both of our pipelines, as Luca described, our binary and our multi. In the binary pipeline, there are 2 derivative images that are created. There's an image that does the actual inference and an image that does the LIME analysis. Here I've opened the binary inference, and as you can see, burnt into the image are both categories, normal and other, with their associated probability scores. Of course, the image is being resized again to deal with the latency issues that we'd be facing with the infrastructure in rural India. The other output of our binary model is the LIME inference, sorry, wrong button. And here you can see, as Luca demonstrated, the parts of the image that weighed most heavily towards the finding, in this case, the classification of normalcy. Now, it's not ideal. We would like our model to be more robust. LIME typically has issues with stability and precision, but we're facing a more extreme case here because for the purposes of the demo, we have to limit our sampling to 100 samples, basically 100 megapixels. And that in itself will take about 30 seconds, as you'll see. To do a full inference with the Lime interpretation takes about 2 minutes. And we wanted to cut down on the latency for this demo, so we're not going to have as good a performance as we would normally have. Then the third derivative image that we have from our pipeline, this is from our multi-class pipeline, is the image that actually has the multi-classification associated with that. And as you can see here, out of the 6 classes, the top 3 are ranked from top to bottom, normal being the highest ranked classification as we would expect with the image resized. So that's with a normal image. Let's move on to a live demonstration of a atypical image. First, I wanted to highlight again one of the advantages of using the DICOM format. Here you can see the metadata that's associated with the file that's readily accessible by the physician as they're doing their studies of a particular patient. We can see that the image has already been submitted, but unlike in the last instance, there's really only one that needs to be processed, so we're going to do that right now. We're going to send this image first to our first step, which is the binary classification phase. And we can view the progress of this pipeline through this workflow. First, we see it being converted to PNG, then resized. And now we're in the actual inference stage of our pipeline. And this is doing 2 things. It's doing the inferencing, and it's also doing the Lime analysis. And it's really the Lime analysis that takes the longest part of this process, about 30 seconds. And that goes through about 100 samples. Now we're complete. We can go back and we can see the pipeline concluding. It's converting the PNG back to a DICOM image and registering the DICOM image with our viewing service. If we go back, we can see now that there are the 2 derivative images that were created as part of the inference pipeline, and we can see what the results are. Here we see the Lime analysis, and it's highlighted the area of the lung that weighs most heavily towards the finding of other. Again, assisting the radiologist with understanding and interpreting the results of our model. And then opening the other derivative image, we can now see that this is the binary model. And again, the purpose of this is to break the image into 1 or 2 classes, and here other at 100%, so it's acting within our expectations. There's one final step in this pipeline, and that is the multi-classification inference piece. So we'll go to, again, the original image, and instead of sending it to step 1, if in this instance we find that there is an issue with the lung chest x-ray, we'll send it to our multi-classification model, which is a separate pipeline. We can follow the progress of the pipeline as we did with the original. This is a shorter pipeline. It does not have the Lime analysis associated with it, so we'll process more quickly, as we can see. It's already in the PNG to DICOM conversion. Now it's registering the image with our image viewer. Heading back to the home page, we see that indeed the image has been processed. And if we view this image, we will see now it has the multi-classification labels from highest to lowest, with other ranked at 99%. That concludes my demonstration, and I'll hand it back to Hirsch to finish this off. Thank you.
All right. Yep. Can you guys see my screen again?
Yep.
Oh. There we go. So in terms of, okay, what's the long-term impact? What are we going to do with this? So we've been working with Dr. Parthiv Mehta, who was Prime Minister Modi's pulmonologist in the past, and he's given us access to 1,800 healthcare professionals, and all of them will have access to our pipeline, and they've started to pilot it and demo it. As I already mentioned, we're supplementing the doctor's decision-making process, and we're prioritizing which images to look at first. And on top of that, there's really no cost to doctors. For the next 6 months or so, both Marcus and I have our IBM credits where we're running this off of, and it kind of falls under there. After that, we kind of did a rough estimation of what the cost would be like if we wanted to sustain this pipeline in the long run, and it came out to about $900 a month. And so it's something that's definitely reasonable for the impact that we're having. The other thing that I want to touch on is this is going to be used in educating the future radiologists as well with the Lyme analysis we've done. As I mentioned earlier, the radiologists, even senior radiologists, are predicting at 80 to 82%. We've been predicting at about 90%, and so we're kind of much higher than the industry standards, and we can help people think about how to predict these images in the future as well. And with that being said, I want to thank everyone for listening, and happy to answer questions as well. Thank you.
Excellent. Thanks. Judges, questions?
I guess I can start again. Thank you everyone again for amazing presentation. Projects like this is highly impactful, especially during a time like this. I have a couple questions. So first one, I just want to make sure I have it the correct understanding. At the beginning of the presentation, you mentioned that the public set is often mislabeled. So is the current set you're working with, is it purely being provided by medical staff in this case? Okay.
Yeah, it's provided by our team, and it's all hand labeled and double checked to make sure that everything is correct.
Okay, awesome. So then you spoke about sort of optimization on accuracy. I want to get an understanding, did you guys, I know you guys used a model that sort of boosted recall. Is there a reason now to prioritize on recall versus just looking at overall accuracy when you're looking at which model to select?
Yeah, that's a good question. It's a very good question. The question we'll be juggling with pretty much for the entire length of the HAR project. Shall we look at recall? Shall we look at precision, accuracy? We started off saying recall is the real thing we want to target. Why is that? Because we just started, from the assumption that, recall, you're essentially measuring or limiting with high recall false negatives. And that's really what you want to have a good grip on in this specific context. But then the assumption here, when you make that decision, is that essentially you're assuming that this medical staff will just rely 100% on the results of this pipeline, which turns out not to be the case. As Hirsch mentioned, this is supposed to support medical staff as opposed to replace it. So in that sense, even though there may be false negatives there, we know there will always be medical staff there, double checking the results, having another look at those. In that sense, we thought that perhaps in a situation where you want to help prioritizing it, recall, even though it's still an important measure, has a bit of less relevance. What you may want to really boost is precision. So to say, you really make sure that whatever you're prioritizing is indeed a condition you want to look at. That's to reply to your question, generally.
Thank you.
Unmute. I have a question that's related. I know we have a bit of a conversation happening around false positives and false negatives, and I do appreciate that there's a human in the loop oversight, but we are talking about a prioritization algorithm, right? So essentially it prioritizes, and as the situation was set up in the beginning, you'll have hundreds, if not, hopefully not, but thousands of x-rays to look at. It's prioritizing for them. I do appreciate that a human will look at it, but a human may not look at it until a week or 2 weeks later, in which case it might be too late. So I would encourage some more thought into your false negatives and how to approach them. And one thought I may have, because I have actually in some of the client work that I've done, not necessarily in COVID, but in other spaces, have actually sacrificed to have an increased number of false positives in order to reduce my false negatives. And that's one way you might approach. In other words, yes, there will be x-rays that are tagged as potentially having COVID that don't have COVID, maybe at a higher rate, but you would that's a good trade-off to have. I would rather a doctor look at someone who's healthy and say, no, this is fine, than 3 weeks later say, oh, shoot, this should have been prioritized higher. So that's one suggestion. A second thought is actually something that was just posted. I was going to ask how, and this is my naivety, I'm not a doctor, how does a chest x-ray help diagnose COVID, or how does that help with COVID?
I just want to respond to your first part. Again, I agree. During the project, we did try an ensemble approach for the first stage in the binary classification where you essentially would label an image normal only if there is consensus across all ensemble members. We saw that experimentally there was boosting recall by, a considerable amount. So that's definitely something we can consider for, future work on this pipeline. Thank you so much. And I agree with you.
Yeah, I can take the second question. So you're right, we can't diagnose COVID, but our algorithm under the atypical pneumonia can detect COVID-like symptoms. And then, a doctor would then maybe prescribe a test or something else would happen. What the issue is, and I didn't mention this earlier, is that a lot of people have their X-ray images. Not a lot of people have access to these COVID tests. So that's kind of the use case for the project that we've built up.
So this might actually be a good lead-in to my last question. So this seems to actually be a bit computationally complex, and we are talking about a place like India where there's going to be a wide variation in accessibility, and in particular, my concern is that you're going to see COVID spread like wildfire in the lowest income areas and neighborhoods. How might you suggest supporting, a low-income slum doctor, for example, right, that needs to treat patients who's not going to have great computing equipment or good internet access?
Yeah, that was a primary concern we had throughout the beginning, even from collecting the data, keeping it as simple as possible, and reducing the amount of technical knowledge that's needed. So we have a one-drop click portal to collect the data. The access itself requires no installation. It's all web-based. So it's password accessible. So the doctor in rural India would be able to point any web browser to our viewer to be able to start using the service. Our biggest concern is latency on the upload with 5 megabyte images. It does take a lot of time on poor network systems. Outside of a client-side solution, there really isn't much we have control over. We did everything we could on our side in terms of the service side and download latency to reduce that. So we took these 5 megabyte images and we reduced them to kilobyte size, so that the processing speed would be much faster and less of a burden on the network system. So we did definitely acknowledge that as a limitation. And as another next step, we did explore using very common services throughout India, like WhatsApp, I think it's called Twilio, and an app-based image viewer as well, so it could all be done on an iPhone. And I'm happy to say that the DICOM format and the DICOM registration method would work exactly the same way with that service as it does with a web-based service. So a mobile platform would be another way to tackle that solution.
Great, thank you. Thank you for your thoughtfulness to that part of the problem.
Excellent. Thank you very much, Team COVID XP. Next up, we have BotBot, the AI Dancer project. So BotBot team, whenever you're ready, go ahead.
Thank you. I was seeing the presentation. All right, great. Good morning, good afternoon, good evening to audience from all over the world. Great presentations to the previous two teams. Thank you. They are all really interesting and meaningful projects and topics. But now we want to relax everyone and talk about something fun. And we will give you a brief introduction about the team and talk about the problem and opportunity we're working on. And we'll let you see our users so you understand what our product is building for, and talk about the tech behind the scene, how we evaluate the model, give it more time and resources, what we'll be working on in the near future, and take a walkthrough of the website, and so you will see how product actually works. So ta-da, this is the team. Surprise, we are human beings, not robots. We are a group of students at UC Berkeley creating BotBot, the AI dancer. Think about this. What if there's an app that could create new dances from your best moves? We use video input to generate custom dance animations to amuse you and your friends. And you don't need to have the technical skills to create custom dance animations because our machine learning model will do the job for you. Are you excited now? So let me pass it over to Stephanie and talk more about why we choose to work on this problem.
Thanks, Sally. So what about the social distance? Dance is a universal language of all cultures. It is how we express joy, love, power, and rebellion, and even grief. It is an inescapable part of the human experience. But the way we dance is being disrupted by COVID. Social distancing is changing the way we interact in all spheres of life. Tech that allows you to interact with others is more important than ever in these times of solitude. So what is changing? COVID is causing the market potential for dance-based technology to accelerate. Search on Instagram for the dance hashtag and you'll get 1 billion different videos. Dance is also offering both a mental and physical outlet right in your living room. And finally, TikTok. TikTok is a growing market with just a single dance recreated 2 million times across the world. Little did we know how much attention this app would get when we started this semester. Creating simple and visually appealing moves is key to going viral in this platform. So now a bit of a test for the audience. If you're ready, I want you to answer a question. Which one is the AI? Is it A, is it B, or is it C? The answer is C. A is actually the state-of-the-art human pose tracking to animation technology. And like most current dance technology, there's no creative license taken by the computer. You can find this on your mobile phone or on websites. C is one of our earliest models. You can see that the AI had learnt the position of the body and some movement that can be considered dance. And I, as a dancer, was so intrigued by this output that I had to head to the studio and try and embody this movement, as you can see in B. The challenge to recreate this very skeletal but random movement exactly was mind-bending and a great distraction from my circumstances. So other than me, who are the users of our product? Meet Nina. She is a professional dancer looking to broaden her creative practice. She's more open to out-of-the-box solutions such as the one that I took to the studio. And next, meet Bell. Bell is new to dance and uses it to socialize. He wants to challenge his friends to copy his AI bot and have a laugh. I will now pass to Laurel to discuss our MVP and our modeling approaches.
Thanks, Stephanie. So now I'll give you a little tour of our product. Our user uploads a short video, maybe 15 seconds long, on our website, or they can choose a video from our library of public dances, like this one of a YouTuber performing a hip hop dance. The user is presented with the output from the open pose model, which is one of the cornerstones of our product because it extracts from the raw pixels of the video the key points that represent the human body. We also present the user with their dance after it has been translated into our vocabulary of dance poses. Instead of just returning the final output to our users, we chose to give the user all of the output our models generate along the way. The LSTM model is our baseline model, and we were not initially planning to present the output of this model or of our vocabulary of dance poses to our user, but including the output from all of our models not only increases entertainment value for our casual users, it also provides additional inspiration for our more sophisticated users, the professional dancers that Stephanie mentioned. Finally, we present the dance generated by our GPT-2 language model. I'll talk about all of these models in more detail coming up, but the GPT-2 model takes the vocabulary of dance poses as input and generates a novel dance choreography in the same way that it generates novel text output after being given an input of a sentence or a paragraph as context. Now I'd like to cover the technology in a little more detail. You've already heard about Open Pose. So once we've extracted the key body points using Open Pose, we then scale and center the key points so that all of our data is comparable. So a dance performed 20 feet from the camera is the same scale as a dance performed 10 feet from the camera, or a dance performed on the left of the screen is the same as one on the right. To create our vocabulary of dance poses that you saw in the demo video, we fit a k-means clustering model on our entire data set of almost 15,000 dances and over 35 million individual frames of video. The clustering model assigns each frame in our data to one of 52,000 clusters, and we average all of the frames in a given cluster to create a mean pose for that cluster. The scaled and centered array before clustering is sent off as our input to our LSTM model, which takes one frame from the user's input dance and generates a series of frames, each predicted from the one before. We render these frames as our bot dancer to create our first novel dance. Our second novel dance generation model is trained on our original dances after we translated them into the clustered vocabulary of dance poses. And the reason we chose to do this is so that our GPT-2 language generation model will have a limited vocabulary, and it can learn patterns in the dance in the same way that it learns patterns in language, verbal language. Before this clustering, each video frame in our data was completely unique. So to make the interface with the GPT-2 easier, we assigned a unique fake 5-letter word to each of the 52,000 poses in our vocabulary. In order to generate a novel dance, we first use the trained k-means model to predict the cluster assignments for each frame in our user's inputted video. And we translate this into a short snippet of text, which is used as context for the GPT-2 text generation model. The model outputs new text that we convert back into video frames. And like we did with our LSTM, we render the new frames as our bot dancer to create our second novel dance. Our GPT-2 uses a sparse categorical cross-entropy loss function, and our best performance was an accuracy of about 60%, which is not that far off from the industry standard for a number of domain-specific language modeling tasks. For the k-means clustering model, we relied on spot checking frames from our test data, and we compared the original pose with the mean pose of the predicted cluster. And here are some of the examples. You can see how the k-means model sometimes doesn't get it right. But for us, the main focus was entertainment and inspiration. We're not trying to create a new dance that someone would find indistinguishable from a professionally choreographed dance. We welcomed the unexpected output. Art is subjective, and there's value in the psychedelic outcome as much as in the polished dancer. So a few key technical takeaways. First, we attempted this project to tackle video generation in a novel way, and we're unaware of anyone exploring language models as a tool to generate new dance. Second, we feel like we would have gotten better results if we had focused on one specific genre of dance, but this would have required curating a data set from scratch. We like to think that training our GPT-2 model on a variety of dance styles is kind of like training it with language input that starts with English and then transitions to French and then Greek and then Russian and so on. Our model performance improves to a peak, but instead of plateauing, it starts dropping, and it continues to drop to a pre-trained levels. And we wonder if maybe that issue of multiple genres is contributing to that drop. Finally, scaling and clustering our data were keys to improving the performance of our models. And now I'll pass it off to Naga, who will talk about our lessons learned.
Thank you, Laurel. I would like to share some important lessons that we learned over the course of this project. No one should underestimate how much trouble you can run into when integrating a pipeline. Data engineering is definitely a critical task in any data science project. You should always be like a detective. Debugging is really important, and it was hard sometimes to know where exactly a mistake is happening in our pipeline. Pre-processing is another hard part, especially when it comes to videos in our learning, as we were gathering data from videos and transforming them into arrays. We burned around $2,000 to try pre-processing data using a script provided by NVIDIA Labs and didn't get the results we wanted. So always try with a smaller data set, but how smaller is enough is always a difficult question to answer. So we would say data collection and cleaning should always be a priority. Obtaining quality data is harder than data modeling. Once you have a good amount of clean and pre-processed data, your job is at least 25% done. Computing power and memory are important bottlenecks in our project. The project moved much faster than we thought because of shared responsibilities and collaborated work and helped us achieve our deadlines without any problems. So teamwork is really important. Always focus on the smaller issues, which can cause a lot of trouble in the final stages of the project. Now, I would like to share our future plan for the project. For the next quarter, we will definitely focus on clustering and getting a cleaner data set and train the models with a single dance style so that users can get better output. For the quarters in 2021, we would definitely want to create a user-friendly mobile app and also let users choose the avatar of choice for the output dance. There will always be a constant focus on the performance of the pipeline. Currently, our latency is a bit high, and we would like to set a certain threshold to get the output. With more funding, we definitely can achieve these results in less amount of time. I will pass it off to Shirley to finish up our presentation.
Thank you, Naga. So to wrap up, we really want to bring up the concept that why we think this is really important, especially during this difficult time to dance is to live. And what we are working on is the cutting edge language models to generate dance. We believe no one else has been working on this using this novel way. But most importantly, we have been working on this when we started this project. We really thinking about how we can make AI more accessible to everyone, to artists, to people who do not have technical backgrounds and can use AI and machine learning to generate new ideas and inspirations. Now, without further ado, I would like to share with you how our website. I was still seeing my screen.
Yes.
Okay. Awesome. So as you see, this is the website that we have built, and then we are targeting inspirational seekers or YouTubers or TikTokers or even professional dancers. For all the information you are seeing in our presentation, you can find on our website. Most importantly, I want to bring you to the try out here. On the website, our users can choose to upload their own dance, like an MP4 file of their own dance to see how it works, or we provide users with a library of videos here to see how it works out. For example, this is Nina you have just met on our presentation. And the final output is the GPT-2 model that we are going to give it to our users to see all the final output. However, we also want to invite our users to see other outputs as entertainment or inspirational value. And the open pose model output given the users understand how their key stickers are output throughout the original dance, and even the novel dance on the vocabulary one. Last but not the least, we want to give a shout out to all these people who have given us instructions, insights, and support throughout the journey. And without them, we won't be able to get to this point. Thank you. Now we want to open up to questions.
Excellent, thank you. Judges, questions for the BotBot team?
I had a question on how the GPT-2 part works. So if I understand correctly, so basically you have a dance move, it's sort of classified into a mean dance move that's assigned a 5-character fake word. And then GPT-2 is then used to generate a new language. But it seems like, you know, if it's A, B, C, D, E, GPT-2 is generating, you know, A, B, D, C, E, but that doesn't necessarily mean anything in my fake language. So I'm just a little confused as to how something goes from being assigned these letters to something new being generated, and that something new being generated being translated back into a move.
So the whole dance is not assigned to letters. Each frame of dance, so each frame of the video at about 22 seconds, 22 frames per second, is assigned a word. So each second is a 22-word long sentence. And then you input a whole, like a 15-second video, might be 300 frames of a video, that's going to be 300 words that are input to the GPT-2. And the GPT-2 is trained specifically on our dance language so that the output dance is only words that are in its known vocabulary of our dance poses. So, and it has learned what different poses follow other poses. So it has learned the language of the dance in our input dances.
Okay, got it. Thank you.
I wanted to commend the team for doing such an awesome work. I am in a similar space where I'm working on helping my users tell stories using AI, and it's a challenging space. So I commend you for taking on this problem. My question for you is, dance, my partner talks about this all the time. Dance is such a multimodal expression, right? It's face, it's energy, it's rhythm, it's your cadence, and not just physical movements. Just the way in language, it's not just the words, but overall plot. If you're writing a novel, and how relatable characters are and all of that. So how are you in your long-term vision? I'd love to hear your long-term vision on how are you planning to add this additional modals of expression, creative expression. That's what you're doing, and I'm really impressed. You're helping people express themselves creatively, and this is amazing. But yeah, I would love to hear some of your vision on what's your long-term plans to add additional modals.
I think by using a language model really gives us or harnesses the ability to tap into that. State of the art previously has been LSTMs, and it's a lot more like random learning, and it can't get that deep context that dance has over time. And we can start to incorporate things that will, like, you know, other people have stretched, danced, you know, have hit the beats on the music and things like that. But really we want to try and capture the language of just that movement part a little more accurately as a starting point. And I think that's how we've seen language models transform as well over time. As they've gotten better, they're able to capture more and more context. And so I think it's important to focus on getting that, that long-term dance information captured correctly before we try and approach everything. You're always going to get that interaction from a human in this dance space. And taking it into the studio and taking it further has really been the funnest part of this project.
Yeah, to add to that, we definitely want to tell a story, how we create a summary from using GPT-2 language models. We definitely want to create a story using dance. Like given a video, we want to generate a novel dance that tells you a different story. That is also into our long-term vision. So I also see one more question. So yeah, given that music is in such a large part of dance, especially for those very trendy TikTok videos, do you find value or have plans to integrate musical aspects into the app? Example, integrate dance moves in sync to the beat of a song. Yes, definitely. While we don't learn the music part of it, we only focused on the dance part of it, but we definitely want to embed the uploaded music to it. Or we would like to give users the same way Dub Smash do. Like we would like to give users to add their own music to the dance we generated. That's also, we also have plans for that. Except that, like using videos, it's taking a lot of compute power. So we are somewhat short on that, but definitely we have long-term plans on doing that.
Excellent. Sorry, I think we do have to move on. We're at the end of time for Bot, the AI dancer, but thank you very much. Next up is Excessive Park, Denver. Whenever you're ready.
All right, you guys can see my screen?
Yes.
Yep.
Okay, Hong, take it away.
Good morning, good afternoon, good evening, everyone, and thank you for coming to our presentation. We are the Accessi Park team. It's using computer vision object detection model to find street level accessible parking for people with disability. My name is Hong Yang, and my teammates are Michelle, Rachel, and Richard. Next one, please. I'll be giving you the background introduction of our product. Next one. As of July 26, 2020 marked the 30th anniversary of the American with Disabilities Act. However, in many cities, not all streets are accessible, and accessible parking is not easy to find, and we chose Denver, Colorado as our focus. Next one, please. This matters to a lot of people, and over 30 million Americans have physical disabilities. That's 10% of US population, and 15 million use an assistive aid today. Next one, please. These are some specific statistics, and I'd like to point it out that 69% of people with disabilities have problems finding accessible parking in their community today. Next one. And these are the three types of accessibility problem that we focused on. On top of that, the model detects different handicap signs, stop sign, and no parking sign. I currently live in Denver, and in the beginning of the project, I drove to the downtown area and took photos of different handicap signs. I actually witnessed firsthand the exact accessibility issues in the downtown area. Issues like curb ramp locations have been addressed with data-driven projects in the past. However, no solution currently exists in the market that address all three street-level accessibility problems. Next one, please. Our products was heavily based on user feedback, and we did survey of 8 users who are currently having accessible parking issues. And the top 3 questions are generic questions such as their pain points, and the bottom 3 are specific product related questions as whether they're comfortable using app versus web. Next one, please. And these are only some of the organizations today that address the problem of accessible parking issue. However, most accessible parking solutions relied on individual reports, such as specific parking rules on street level versus facilities. Now I'm going to hand it over to Richard and to give you the vision and mission.
Thanks, Hong. Empathizing with the accessibility problem, our team came up with the vision statement that finding accessible parking should not be a challenge. Our mission to chart accessibility obstacles and accessible parking opportunities with computer vision, Google Street View, and Denver Open Data directly supports our vision. For the visual learners out there, Rachel is going to give you a quick preview of what our mission statement actually looks like.
So this is Accessible Park Denver, our product, and this directly solves the problems that Hong and Richard just introduced. So the user guide will show you everything you need to know. It shows you what's on the map, where it comes from, and how we'll be representing that visually. So if we take a peek over at the map here, we can see all of the information you need to make informed accessible parking decisions. So we can see not only are there accessible parking signs, which there's no other data source for this besides our model or crowdsource applications, but we also have information from Denver Public Data on parking meters, parking facilities, sidewalks, construction moratorium streets, and curb ramps. And then our model is also spotting potential obstacles like roadside lamps. It's spotting where we can't park, and it's also spotting fire hydrants as well. So I'll take it back to Richard, and we'll show some more features of Accessible Park Denver later on in the presentation.
All right, thank you, Rachel. Since most of us did not live in Denver except for Hong, we first took a look at Google Street View images around the downtown Denver area. Unfortunately, not all images were perfect. Some images were blurry, obstructed, and there weren't that many handicap signs that we wanted to detect. We got a classical data science problem of working with bad data. So how did we get through this? After multiple days of brainstorming, our team came up with a plan. Next slide, please. First, we also trained a model to detect street-level accessibility obstacles like lamps, fire hydrants, no parking signs. Second, report the total handicap parking sign in a zip code level in a heat map. And last, use feature engineering, Google Maps, and data visualization to disseminate this information. Next slide, please. With our plan, we divided Denver into 3 batch regions. Then we used ArcGIS Pro to get a list of all lat-long coordinates in all 3 regions. Then use Google Maps API to pull about 200,000 images. Then hand labeled about 6,000 images with label IMG to prepare for modeling. I'm going to pass it on to Michelle, who will talk more about models.
Thanks, Richard. For our model, we use object detection model to identify 5 different classes, namely handicap sign, no parking sign, stop sign, lamp, and fire hydrant. And then the last 4, we consider them as accessibility obstacles, as Richard mentioned previously. Next slide, please. So this slide shows the architecture of our object detection model, which includes 4 parts. The input is where you input your image, and the backbone is the place to extract the feature maps. And then the neck is the place to enhance the feature discriminability. And then the head is the place where you make the actual prediction. So here we listed the most common object detection models. And then among them, we choose the bottom 2, which are EfficientDat and YOLO family for our project, due to they are relatively new and then smaller in size and hence less parameter to optimize. Next slide, please. Between the 2 models, EfficientDat and YOLO v5, we did another round of comparison to determine our final model. And then the comparison condition is shown in the blue box. Here, as you can see, in terms of training time, YOLO version 5 took 50 minutes less than the time taken by EfficientDat. And then our model metrics, which is the mean average precision, YOLO version 5 is significantly higher than EfficientDat. And then also, YOLO version 5 takes less time than EfficientDat in terms of inference time per image. Another thing I want to mention is these 2 models are relatively new. As you can see, the release date is in April and June this year. The fact that we actually ran the YOLO version 5 model just 1 week after the model was released. Sorry, next slide, please. We leverage transfer learning for our model. As you can see from this slide, we hand label the train and test data feed into the model. We use pre-trained weights such as EfficientDat and YOLO version 5. And we also fine-tune the hyperparameter to optimize the model, obtain the trained model. And then we use real images passing through the trained model and then detect the objects and then locate them in our map. Next slide, please. This slide basically shows our model improvement against the different classes for a period of 2 months. As you can see, the orange curve represents the handicap sign class, and then the blue curve is the overall 5 different classes. The gray curve represents the lamp class. In terms of model metrics, the mean average precision, we were able to improve the model performance from 0.45 to 0.693 due to, based on the method we changed in the table down below. And here, as you can see, we basically changed a different model. We changed number of images, we increased number of classes, and we also did hyperparameter tuning and data augmentation. So the key improvement happened when we changed our model from EfficientDat to YOLO version 5, and then also when we increase our number of images from 1100 to 2000. Next, I will pass to Rachel for our app architecture.
Great. So all of the model training and inference that Michelle just talked about, we did that with Google Colab using GPUs. Then we took our inference data as well as Denver public data, and we did some post-processing on our local batch machines. So for the inference data, that included cropping out low confidence images. We also adjust the lat-long positions of the objects on the map based on whether they were either far to the left or far to the right side of the image. So that reduced some overlap and it helped make the positions more accurate. After those transformations, we loaded all of our data into a file system on an EC2 instance where we ran an app using 2 Docker containers, one of them with a Flask backend and the other running a front end with React. Some libraries include React Google Maps and Uber Base UI. And that was being hosted by Node and Nginx. So before I go to the demo, I just want to emphasize that this is heavily driven by our user research. We had 8 initial accessible parking users and then 7 user tests on our MVP. So I'll show you our homepage. So you can actually get to this page with the URL accessipark.com. So here is where you can check out our demo video and this GIF. You can read more about our methodology. You can check us out on LinkedIn, and you can also send us feedback here. So one thing I want to point out on this site is our accessibility ratings page. So this is high level for the city of Denver. Where per zip code do we have the greatest density of accessible parking spots? So we can see in this area we have the greatest density. And so the audience for this page could be local governments if they're identifying where we might want to add more handicap signs. It could also be accessible parking users and accessibility advocates who might be helping people make decisions about where they might want to live, work, and travel that will have accessible parking options for them. So if we go back to Accessipark Denver, we can see here this homepage. So when people land here, a lot of them we noticed tried to zoom out. And so that seems kind of a natural reaction to get a sense of the area. So in response to that, we actually limited the amount that people can zoom. But because there's this desire to explore and we can only populate so much of the map at once, we added a feature where you can click on another spot of the map, it recenters and it populates around that area. And we're generally re-zooming to this level because most people for a given destination, they're interested in parking within a couple of blocks. So for a specific use case, let's say I want to grab a beer with a friend. So for people with accessibility needs, this can be kind of daunting, but with Accessipark Denver, it's easy to see all of the information I need. So you can see if I'm going to this brewery, there's accessible parking a couple of blocks away. And actually one feature I can use here is to check this out and verify that this is in fact the case. And as we can see here, there's not 1 but 2 accessible parking signs, and our model was correct with that prediction. Another place where Street View is useful, over here we can see there's a break in the sidewalk, and actually the street parallel has no sidewalk at all. And if we look over here, this is definitely not an accessible area, and when I'm walking to, or when I'm traveling to the brewery from wherever I decide to park, I won't want to go down either of these streets where they're missing the sidewalk. There are also some missing curb ramps around here. So if we look at satellite, we can see that there's probably some reasonable options for finding street side parking around here, but maybe this isn't the best option. So maybe we want to check out a second location. So by this restaurant, we can see that not only is there accessible parking right down the street, but there's parking meters right across the street. Also, there's the appropriate curb ramps and sidewalks here. There are some obstacles, but if I were to use Street View here, I can, sorry, wrong way. I can check out not only this sign, but I can travel down my route with the street view, verifying that the sidewalk is there, and then I have the ramp I need to be able to get to my final destination. So now, instead of venturing out with a lot of anxiety, not knowing where I'm going to park and how I'm going to get to my final destination, I'm empowered with the information I need to be able to make these decisions. So where can this go in the future? So we really want to empower organizations to not only use this product with people with accessible parking needs, but also to use the data in order to target additional interventions. We also want to empower users. So this could take the form of making our app from a web page into a mobile app. It could also take the form of routing. What's an accessible route from point A to point B? Or recommendations. What are accessible restaurants in my area? We could also integrate recommendations based on weather. So if it's raining, if it's snowing, this area may or may not be less accessible. These are just some potential future features. But finally, we really hope this project will empower data scientists not only to use this YOLO version 5 model for similar tasks, since it worked so well for us and it's brand new, but also to launch instances of Accessipark in their own cities. This is a place where data scientists can really make a direct impact on people's lives and give people a tool that makes a huge difference in their day-to-day anxiety, mobility, and really opens up the world for them. So with that, I'd like to thank everyone, all of the MIDS students and faculty and staff. It's really been a fantastic experience, and we've learned so much from this. And I'll leave you guys with these testimonials and take any questions.
Excellent. Thank you very much. Judges, questions?
I'll start. First of all, thank you so much for the presentation. I have a question regarding the data source. So it seems like the data source that you guys are using are primarily from Google Map and using images derived from Google Map. How would you overcome the issue of image delays? Some of the Google images in Google Map could be there for multiple months, and it's not the most up-to-date data in this case. Have you guys given any thoughts around this?
Yeah, so we've discussed this. As far as we can tell online, there's not a consistent schedule with which Google updates their Street View images, and it varies per area. So probably what we would do is we would want to set a cadence to kind of refresh this data, maybe something like 6 months or 1 year or something like that, to keep it as up to date as possible, as well as the data that we have from Denver public data. We would also want to pull that on a periodic basis. But I think we saw on average roughly yearly Google will update the Street View data, so it's not a very fast
cadence. Have you thought of maybe potentially adding in a user report feedback loop in this case, where if certain things are drastically different, then maybe instead of relying purely on images derived from Google Map, that y'all take user feedback into consideration as well?
Absolutely. So we do have a feedback form on our website, and eventually we want to build out some more direct, like clicking on the map feedback, maybe clicking on a specific icon. But in the meantime, there is a feedback form available for people to send us that information.
Thank you.
Deval, Ruman, questions for the team?
Sharon actually asked the question that I had, so no.
Me too.
I don't have a question. I just want to make a quick comment on the ramp, around detecting ramp and the last mile problem that you solved, and that was amazing. Thanks for sharing that.
Thank you.
Thank you.
Excellent. Well, thank you so much, Accessipark Denver team. Next up, we have Find Your Rhythm. Whenever you're ready.
Okay, can you see my screen? Bobby, take it away. All right. Hello, everyone. Thank you for joining us. My name is Bobby Calzaretta, and I'm joined by my colleagues, Gautam, and Andrew. Together, we are Find Your Rhythm, and we are applying neural networks to transcribe music for learners, educators, and professionals alike. Find Your Rhythm is motivated by how integral music is to every culture, especially now. In the era of COVID, people are turning to musical performance as a source of entertainment and therapy. But independent of current events, interest in learning how to play music is abundant. The majority of households in the US have a musician, and the proliferation of compact electronic drum kits, as well as computer-based music creation software like GarageBand, the means to create music have never been more widely available. Despite this, the means to learn music have remained difficult to acquire. Pandemic-related restrictions to in-person instruction, as well as cuts to school music programs, jeopardize music education. Therefore, having access to sheet music, otherwise known as song transcriptions, is increasingly critical to musical students and professionals alike. Transcribing songs into sheet music is mostly a manual process requiring expertise in music notation. For drum sets in particular, sheet music is limited and expensive, often ranging from $10 to $50 for a single song. This is the deterrent to any prospective drum student. Imagine, you want to learn a new song each week. By the end of the year, you can spend up to $2,600 for only 52 songs. And this assumes you can even find the songs that you want to learn. Additionally, recent efforts at automating transcription have largely been academic when it comes to percussion. The literature is limited to transcribing just 3 sounds in drum set: an aggregated hi-hat sound, a snare drum, and the bass drum. For reference, most beginner drum sets sold at Guitar Center have at least 5 different types of percussion, and experienced drummers typically include even more types. School of Rock, perhaps the largest player in music education, lacks the capacity to transcribe percussion, even though the company provides its customers with an app that transcribes guitar and other melodic instruments. Find Your Rhythm fills this market void. We provide free, quality drum transcription for all. Users will not be limited by their budget or what songs the market supplies. Any song a student wants to learn can be uploaded, and the drum notation will be provided to them almost immediately. Before we demonstrate our product, I want to highlight some key features of Find Your Rhythm. Find Your Rhythm allows users to upload songs in multiple file formats. It isolates the percussive aspects of the song using an approach called Spleeter, and provides the user sheet music in the form of a MuseScore file download, which is a popular digital sheet music format. Lastly, the most distinctive feature of Find Your Rhythm is that it can identify up to 13 percussion instruments common to a drum set. This is 10 more sounds than the bulk of automatic transcription models covered in the literature. With this product, a drum enthusiast can easily acquire the means to learn any song they've been meaning to play. Drum instructors can seamlessly generate and distribute lessons for their students free of contact, and professionals can share their inspiration or leverage the tool to promote their own music. To demonstrate Find Your Rhythm, I'll turn it over to Gautam. Okay, we are very excited to show you our MVP. So this is our website. And then we go to try it. So we have a few songs here that we can play, and we can potentially try and transcribe using this service. So let's go for something like jazz. So that song had only drums and no other instrument. And maybe let's pick something like this. Okay, now let's see how to transcribe these songs. So we go to transcribe now. The first step is to download a software called MuseScore. This will later allow you to visualize and play the sheet music that we generate. We then choose the file that we want to transcribe. So let's pick the jazz one that we heard before and say transcribe this song. Now, one of the things that you could have done was, if your song had only drums, you can choose to select this box here. This is going to bypass any source separation that we do. Now, in the background, the song is getting converted to a waveform array by Librosa, and then getting converted into a Fourier transform. This is then passed to the model, which detects onsets, and the onset detection is translated into rhythmic duration notation.
Looks like we are almost there. All right, so the transcription is complete. And now I click download transcription. And now I can actually play this transcription using a software called MuseScore. Awesome. Let's also try one more transcription. Let's try the transcription of the Highway to Hell ECTC song. So I again go to choose my file. I pick the Highway to Hell sample. And I say transcribe this song. So the only difference in the first one and this is that we split the audio and use only the percussive stem for onset prediction. So it looks like our prediction is, our prescription is done. And we just say download again. So what you will see is a small piece because of licensing issues, we just took a sample. And you're only going to see the drum piece out here because we just created drum transcription. So, and that's just the drum part of the song. So going back to the presentation. So why these features for the MVP? The key selling point of our solution is how accurately it can transcribe. We cannot afford to throw in wrong notes in our transcription. So we had to go with an MVP that produces the best results with a fast time to market. We also had to ensure that our MVP is easy to use for students to start learning. And finally, choose something which would create a seamless experience with very clear instructions. To talk about the model, I turn it over to you.
Of course. So after Gautam shared our pretty cool product, I would like to introduce our technical approach to make it. So more than 400-hour percussion mixture audios from 3 databases covering 20 drum pitches with the labels including at least the information of the onset and the corresponding instrument are used as our train, validation, and test data. Long short-term memory, we call it LSTM model, one of the recurrent neural network model outperform compared with other models such as the decision tree, XGBoost, and convolution neural network based on our study and research. Finally, we land on the bidirectional LSTM model, which further improve our model performance by preserving the information of both the past and the future, which is achieved by running your inputs in 2 directions as shown in this graph. So one is from the past to the future and one from the future to the past. Finally, with the sigmoid neurons output from the model, the peak picking method is developed to detect the onset for each instrument. And finally, post-processing is performed to transfer the onset array to music XML files. So obviously, when I hit the drum, you can hear the song, but you cannot see that. So the analog wave is used to visualize the sound with information of the song frequency as well as the amplitude. I will play an audio with the drums mixture, and you can see the wave change with the sound in this video. So the sound wave becomes more complicated when the audio has several drum instruments playing together. So if only one drum instrument is played, it looks similar to the figures on the left side with the pink and the yellow solid lines. As you can see, the instruments play with the uniform frequency. For example, the pink solid line represents the sound with 2 hertz, which means 2 waves per second. So however, if 2 instruments play together, the waveform is combined as shown in the bottom figure with the green solid line. If we only see this green solid line, it is quite hard to tell what is this sound and what is their frequency. This is where the Fourier transform feeds this gap. With the Fourier transform of the sound wave, we will have the graph on the right side with X representing the frequency and the Y of the intensity. With the 2 sounds overlap, the Fourier transform could show the frequency of the 2 sounds with the spikes as shown in the right bottom graph. But looking at this graph, after Fourier transfer, it lost the very important features for the audio, which is time. Therefore, the spectrogram is applied to combine these two kinds of the graphs together. So here is a short-term Fourier transfer spectrogram we used as our model input. Y represents the frequency, X represents the time, and finally, the color represents the amplitude. With LST model, which is a kind of the time series model, it is important to define the segment length, which is the time window of the input fitting into the model. Here we choose the time segment of 5 seconds. So here we transfer the spectrogram graph to the array. On the right side, each row represents the frequency levels, and the column is the total time of the songs. The amplitude becomes the value in the array. We have segment length of 5 seconds. So in order to avoid two songs are concatenating into one segment, we pack silence with value of 0 at the end of the songs based on the size of the audio. Looking at this array, you will realize each song has same number of the frequency beings, but different total time. Therefore, we transpose this array so that each audios would have same number of the columns. With this shape, it is easy to concatenate all the audios from the 3 database I mentioned before. So for bidirectional LSTM model, we have several challenges need to cover. For neural network with tons of the training, it could memorize the training data set with high variance and low bias. But memorizing is not learning. So we apply several methods such as simplifying models with more data set, adding dropout layers, as well as the early stop to make sure the model would stop in the green region, representing the model is balanced. And eventually, after the model training, we have the first graph representing the probability of the model output with the color for 3 drum instrument, which is hi-hat, bass drum, and snare drum. So apply the peak picking method we developed. We translate the probability from the activation function to the onset for the same 3 drum instrument. And then finally, with the post-processing, this onset array is transferred to the final music XML file, which is provided to the user for download in our app. With this, I will shift to Angel to discuss about our model evaluation.
Great. So we use the F1 score as our metric, as for us, it's equally important to both predict accurate instrument onsets as well as not predicting false positives. You can imagine that if the model predicts notes that don't happen, or if it misses notes that do, the sheet music will not be as good. So here you can see the model results for common instruments found in automatic drum transcription literature, but also note that we chose to focus on many more instruments so that they could be notated, and we still get good results with our model. And now that you've seen what our model and application can do, we'd like to move on to the fun topic of what it struggles to do and how that aligns with our roadmap for future product development. Given that our MVP was designed, tested, and deployed to a cloud infrastructure in only a matter of weeks, we started with a general all genres, all drum set instrument approach to prove the concept. And as you can imagine, with so many different sounding instruments in the real world, our model might have a hard time with some of them, and namely electronic sounding instruments is where we find this. To illustrate this point, we would like to play for you 3 audio clips of the exact song played on different drum kits. The first audio is played on a classic rock kit. The next audio is a 909 kit, which is much more electronic sounding. And we can plot the frequency distributions of several common drum instruments and view these frequencies side by side. Because there's such a variety of sound in the real world, one of the things we're planning to work on to improve model performance is classifying drum kits as electronic or acoustic based on their sound. We can then use models which have been specialized for the scenario at hand. And this approach doesn't just stop at the drum kit either. We can use model F1 scores not only on different kits or instruments, but aspects such as genre as well. As you can see, our current generalized model does not fare as well for songs under the soul groove genre. However, training a model specifically on soul groove audio with the same variation of drum kits, drummers, etc., yields much better F1 scores. This applies to use cases where it is necessary to use source separation like splitter to split the percussive elements of a song as well. Models trained on drum-only audio would fare worse on split audio transcription and vice versa. The key here is specialized models to boost performance. And we're enthusiastic about this classification and ensemble approach, not only to boost the performance of our app, but also because it opens doors to things that companies like Spotify have been doing for years, such as recommending more music for instruction based on a user's genre and drumming style preferences. Additionally, we can expand the capabilities of our app using the same approach to give user feedback associated with the musical piece they are learning and letting them know if they're playing the right notes in the right rhythm. As a music instructor, this allows you to spend more time focusing on technique and theory instead of finding music for your lessons. And as a student, this opens up doors to new music you haven't encountered before. Either way, automated music transcription enables more musicians to explore vast areas of musical development. And with that, we'd like to leave you with what started this project and drove us to develop the app. Free sheet music transcriptions for all musicians, regardless of musical tastes, proficiency, or budget. We encourage you to upload music of your own to our app and let it enable you to learn any song of your desire. Thanks for your time, and let us know if you have any questions. We'd be happy to answer those.
Great, thank you. Judges, questions?
First of all, thank you so much. I have a more tactical question as to why you guys choose drum as for your MVP. I would think that out of majority of the instruments, it may be the toughest for a beginner to get a drum set to start learning. So or is this specifically targeted at established musician or people who already know the instrument? So would love to hear your thoughts on this.
Yeah, I can take that. So the reason, first of all, this approach can definitely be extended to other musical instruments. Gautam, if you go to our FAQ, I think we addressed this, but we chose percussion because there's a significant market need for percussion transcription and percussion sheet music. If you're learning how to play the guitar and you want to learn a Def Cab for Cutie song, you can just Google that song. And you can probably find free transcription. I don't know the quality, it might not be very good, but you can find it. And that's not the case for percussion. So there's a market need. And to your second point on, is this for new students? Is this for experienced students? This is really for anyone looking to dabble in a musical instrument, whether you are a musical professional, whether you're someone like me who has taught music lessons, who's not a professional but is an enthusiast and just wants to learn more songs. So it kind of allows you as a user, regardless of your proficiency, to upload music that you want, even music that you have created yourself, and get sheet music for that. And that was kind of what drove us to develop this.
I would also like to add that there has been a wide adaptation of electronic drum kits, which can be more affordable and can take up less space. So interest in drumming has increased, as has the means to actually start playing drums, either with an electronic drum kit or software like GarageBand, where you can use your keyboard to make the percussive notes.
I have a question on sort of translation to other music media and instruments. So I could see one benefit of working on percussion and drum, and this is not to oversimplify the difficulty of playing the drums, but for example, vocal or guitar, etc., has a huge range of notes that you might have to detect. What might be some challenges you would face in trying to translate this into something like identifying the difference between a sharp and a flat, for example, in playing a musical instrument or singing a song, and how might you think about addressing those challenges?
I think I would like to take this question first. I think it's really nice suggestions for that, and it's really good question for that. And we're thinking about that. And first of all, following that question about the drum. So the reason we do the drum is we mentioned we do the research. There is other groups already do something related to the piano or guitar, but we realized for the drum, they don't do a lot of jobs for that, and only 3 drums instruments is studied. And another thing is, as you mentioned about the vocal, the guitar, and the piano, the plan for our version 2 is that we have the splitter, right? So we will have the splitter to split that to the drum only, or to the guitar, or to the vocal. And with that, we will have our training data set after the splitter, and we will use that to create the different music transcription based on that. So I believe for this kind of the model, it's still possible to apply to the different kinds of more complicated. For example, the piano, it will have the 88 notes. So we will have more output, and the frequency, maybe it's much more close with each other. So for that case, we have to use the MuseScore as Gaudium shows before they can create the specific notes. And we can use these two specific notes to generate the training model for the specific notes. That would be much easier for the model to handle that. This is our plan and understanding for that.
Thank you.
Sure.
I have a question about the transcription and sort of the parameters and whether or not you've sort of explored sort of the boundaries of the transcription. So for example, like how does it handle different time signatures that aren't, 4/4, or how does it handle tempo changes that are like intentional, not just sort of like a result of, poor, like kind of, drummer error, I suppose.
Yeah, I can take that. So good shout on the time signature, right? For our MVP, we focused on 4/4 as the most common time signature. So, a student uploading something crazy like 13/16 time, we would need to, in our roadmap, we didn't talk about it in the presentation, but we've got things like using Librosa to, use their beat tracking mechanism to figure out what the measure, for each measure, what the time signature is, right? Because one measure might be 4/4, and then the next one might be 7/8 or something like that, right? So a lot of this is leveraging open source packages like Librosa to identify that. But the second part, as far as tempo and time signature, is we'd like to allow user feedback into our app where if you look at the FAQ slide, you might have something where you purposefully change the tempo or where you purposefully change the time signature or whatever. Or maybe Librosa just mistakens what the tempo is or the beat is. And taking certain input like the beat and the time signature, whatever, from the user, we've shown can result into more accurate sheet music. So going forward, that's something we want to lean into, which is user feedback and different mechanisms of Librosa as well.
Great, thank you. Other questions? Well, okay, thank you very much, Find Your Rhythm team.
Thank you.
Next up is high-res irrigation detection. Whenever you all ready?
All right. Yeah, let's get started. Let me share my screen.
All right, welcome everyone. We're the high resolution irrigation detection team. We've been very fortunate this term to work directly with the world-class environmental science department here at Berkeley, specifically Professor Paulo Diodorico and Drs. Lorenzo Rosa and Manuela Girota to kind of help us hone this globally impactful project. Our aim is to push the frontier of knowledge in global irrigation. And this is important for a number of applications. For example, from a public policy standpoint, irrigation data can help with monitoring and ensuring sustainable water usage. The data can also be used to determine water rights laws for things like properly valuing the price of water. Additionally, irrigation can impact weather, precipitation, and temperature, and can have an impact on climate change. The current data on irrigation has a number of issues. The source of truth, coming primarily from data captured sporadically by countries, is out of date, unreliable, and at a lower resolution than what researchers would really like. Our objective with this project is to create a tool to generate very high resolution maps on what is irrigated and not irrigated. To get a feel for this resolution, the image at the top, the red quadrants, is roughly the resolution available today. What we have developed is shown within the yellow breakout. The purple boxes are roughly our output resolution of 30 meters. At this higher resolution, researchers can start to be more precise about their understanding of the nature of the problem, to create and track solutions. Next slide.
Our objectives shape our goals, and our challenges shape our approach. To extend the work of others, yet set resolution at 30 meters, inference runtime would be 16 years. Our solution is to deliver a high-resolution, real-time inference on a small area. To run supervised ML algorithms, source of truth is required. This exists at 8 kilometers and 1 kilometer, yet there is nothing authoritative globally at 30 meters. Our solution is to run unsupervised learning and use creative evaluation methods. Temporal signatures in agriculture can confound irrigation determination. Our solution is to selectively leverage features that are low collinearity and high correlation to crop health. Domain knowledge heuristics will aid further categorization.
In order to obtain 30-meter scale resolution, we have leveraged Sentinel-2 dataset. These images are obtained from ESA satellites that collect high-resolution, multispectral imagery. Earth observation satellites acquire digital images in a small spectral band. The bands are grouped into wavelength regions based, among other things, on the region of the light. We use climate dataset for monthly climate data. Since temporal signatures behave very differently across the globe, for example, Jan can be farming season for India, but is ice cold in Idaho. So we want other climate information to help with building the ML models. GFZ30 helps identify cropland at 30-meter resolution. GFZ1000 has irrigation labels at 1000-meter resolution. And we access all these data sets via a single sign-on provided by Google Earth Engine. Next, please. Using satellite imagery, we can derive various vegetation indexes to be used as features for our predictive models. Some of the standard vegetation indexes are NDVI, SAVI, and EVI. These are different spectral indexes to calculate vegetation health and detect abnormal changes in the vegetation growth. It helps differentiate vegetation from other types of land cover and determine its overall state. For example, shades of green indicate normal to dense vegetation and red is bare soil. Every index has its limitation. NDVI is sensitive to the effects of soil and atmosphere, and that's why it's recommended to apply additional indexes for more accurate analysis. PCA correlation heat map for 2018 data shows that NDVI and SAVI are fully correlated. EVI is not highly correlated with either. However, prior research has shown NDVI and EVI produce equivalent classification results. Hence, we used NDVI along with precipitation and max and min temperature features obtained from TerraClimate. Next, please. However, it is not easy to compute data at the high resolution we need for the project. There are multiple limits we face when trying to download data at 30-meter scale. GE limits of 5K images per pull, Folium not allowing rendering of images with over 5K overlays, and read limits per minute. For example, as we can see, downloading the pixel level data for, say, Argentina would be near impossible given the time and compute limits. Collecting the images beyond a month at 30-meter scale hits the GE limits. And if we try to read NDVI information for this area, for even a day, we face computation errors due to pixel read limit. Next, please. In order to use unsupervised learning, we utilize vegetation index for classifying clusters. Human eye cannot visually perceive NDVI or near infrared as is. So we use a calculation based on the band reading to determine VI indexes across geographies and time periods, which is then fed as a data frame into models. Based on EDA, we found that clustering is effective in identifying areas with different NDVI signatures. Next, please.
Thank you, Suna. Here's our modeling pipeline for an area of interest. We made a simplifying assumption that only cropland can be irrigated and non-cropland cannot be irrigated. This assumption aligns with the project motivation of understanding global agricultural irrigation. Although someone's lawn may be irrigated, it's not the focal point of this project. So the first step of the pipeline is to weed out non-cropland pixels and pull monthly vegetation index on the remaining cropland pixels. Based on our EDA, as Sunat mentioned, we learned that unsupervised clustering algorithm can be effective in separating different group of NDVI patterns in a local area. What unsupervised clustering algorithm does not tell us is which of the cluster is irrigated, if any. So we need to apply some algorithm to figure out the cluster label. The algorithm would take cluster centroids as an input and spit out a label for each cluster. We tried 3 different algorithms to determine the cluster labels, and we will talk more about them in the next 2 slides. Our final output is an interactive map where each cluster is colored differently with a label of either irrigated or rain-fed. Next, please. I will first briefly talk about our first 2 attempts at determining clustering label. We built multiple supervised learning models on a global sample of data using monthly NDVI data as well as various monthly climate data. Our target label is GFSAT 1000, which provides irrigation label at 1,000 meter resolution. The best validation accuracy we got was 71%. Because the vast majority of features going into the model were climate attributes, which are very similar for all pixels in a small localized area. The supervised learning model was not able to distinguish between clusters in a small region. Our second attempt was to calculate the similarity between each cluster centroids and the expected irrigation NDVI temporal pattern based on GFSAT 1000. The issue we found is that in a lot of the test cases, there was virtually no difference in NDVI temporal signature between irrigated and the rain-fed cropland in GFSAT 1000. As a result, the similarity model did not perform well. Next, please. Our final model is the heuristic approach. We identify crop season based on NDVI peaks. The crop season is considered irrigated if it satisfies 2 criteria. First, NDVI peak is greater than 0.3. Second, the precipitation during the crop growing season is less than its water need. We came up with the NDVI threshold and water need estimation based on various research. There are a number of advantages to this approach. First, this heuristic approach can be applied to any number of clusters independently, so it's scalable just like the clustering model. We are also able to estimate the number of crop seasons in a year and the months of irrigation. Last but not least, it's easy to incorporate additional research on NDVI threshold, water need by crop type, etc. Next, please.
So as we've alluded to, there is no easily accessible source of truth of irrigation at 30 meter resolution. So we had to be more creative with our model evaluation methodology. So to help us evaluate our model's performance, we pursued 4 different approaches. So first, we conducted an expert user study with 2 UC Berkeley environmental science researchers and professors, Lorenzo Rosa and Manuela Girotto, who gave us some positive feedback about our model results and package design. Second, we made use of a crowdsourced irrigation data set from croplands.org to compare our model's predictions against, and we selected points from a geodiverse sample around the globe. Third, we compared our model's irrigation predictions against a few cases from GFSAT 30's irrigation data set in India and Australia. For this, we also used the croplands.org crowdsourced data to act as the source of truth to compare our model's accuracy against GFSAT 30's. And fourth, we created a custom metric to evaluate the consistency of our model's output. So we test consistency for a given input region by creating 9 new phase shifted input regions. And of the points that overlap with these slightly shifted regions, we test how often our model makes the same irrigation predictions. So for the case study with crowdsourced irrigation data, we sampled 25 points from this data set to compare our model's predictions against. So we made sure that the coordinates we sampled were from a diverse range of geolocations and countries. The results of this case study were very promising. So our model correctly predicted the irrigation status of 23 out of 25 coordinates. So this result is great, although we must keep in mind the small sample size of this case study.
The next course of evaluation is 10 select localized points for which we have both a crowdsourced label and a 30-meter GFSAT label. That gives us the information we need to evaluate our model, which is in the far right column, relative to the GFSAT model, which is second from the right. Despite known precipitation data issues in this region that we believe are causing some misclassification, we accurately classified 7 out of the 10 points compared to the 8 out of the 10 from the GFSAT. Honestly, with such a small sample size, we aren't hanging our hats on any accuracy figure here, but taken in conjunction with the prior slide, we feel pretty good about the performance of the model. Next slide. The results of our consistency evaluation methodology are shown here. Again, the idea here is to perturb the input area in each direction and observe the output changes. The overall average consistency is a solid 97%, but I call out a couple of our lower performing areas just specifically to double click on what's going on there. As we dug deeper into Ukraine and Saudi Arabia, we noticed that the model is getting confused by different irrigation patterns, possibly some broken pivots, and areas growing multiple crops. Each of these creates some unexpected noise in the NDVI signatures, but ultimately the model is very consistent in its output results, which is a positive sign. Next slide.
Next, we'll do a quick demo of the Python package.
Irrigation 30 is delivered as a publicly available Python library. Installation of the library can be done using the pip terminal command, pip3 install irrigation 30. Further details regarding installation of the irrigation 30 package, as well as the demo notebook we will walk through, can be found here on irrigation 30's GitHub repo. Now we move to the demo notebook. To minimize lag, all cells have already been run. First, the user imports the irrigation 30 library. Next, the user authenticates with Google Earth Engine in order to leverage their API. Once the token is saved, the user is ready to instantiate a model. For this example, we'll be looking at a location in Idaho. The area of interest is defined by the target coordinate and the edge length of a bounding box surrounding the coordinate. If desired, one could alter the number of clusters cropland is divided into, or the year of the data. Now we advance through cells and read results. Cluster 0 is shown in red. This cluster is characterized as a single annual cropping with irrigation occurring around June. Cluster 1 is shown in blue. This cluster is also a single cropping, however irrigated in July. The information can be explored further by toggling map layers. The user can toggle the bounding box, irrigation prediction, Sentinel-2 RGB images for various quarters, a third-party irrigation inference at 1,000 meters, and monthly vegetation indices. If the user needs more information about the region, we can see the cluster's NDVI temporal signature data, regional precipitation data, and temperature. If the output the user desires is data, a GeoTIFF can be ported to Google Earth Engine as a user's asset, or otherwise to their Google Drive. A write-up of the project can be found on our website.
Cool. So as for future work to continue this project, the next step would be to get queryable access to GeoStat30's new irrigation data set, which although is limited to certain geolocations, would still allow us to conduct more model evaluation at a larger scale, even open up new doors for new model development. We could also pursue more complex versions of our heuristic model so that the thresholds for NDVI and precipitation can change depending on known crop types and weather patterns in different geolocations. Lastly, we could also pursue alternatives to Google Earth Engine to circumvent the compute limitations. So you can learn more about our project and our Python package on our website. The URL is listed here, as well as Berkeley's Capstone Summer 2020 website. We also want to extend our thanks to everyone who helped with this project, including environmental science researchers and professors Paolo, Lorenzo, Manuela, as well as our instructors Alberto and Puya. Lastly, some MIDS alumni Deepak and Eleanor. And that concludes our presentation. We'll open it up to Q&A.
Excellent, thank you. Judges, questions?
I can kick off. I just have a few logistics questions. Why is the 30 like the number to meet or beat or to achieve?
I guess I can take that one. So it kind of, we came to 30 with some discussions, particularly with Lorenzo, kind of our customer for this. You know, obviously our current order magnitudes, you know, the 1 to 8 kilometer range. it was, obviously he was kind of pushing for it as much as possible. And we kind of had some trade-offs between what is actually computationally feasible and what gets us to an area where it gets useful to him. So if we're talking irrigation of croplands, somewhere in the order of magnitude of 10 to 100 meters starts to get where you can talk about specific pieces of cropland, which is a use case that I think he was thinking of. So that's where we got to that order of magnitude desire. And then it was just kind of some horse trading of, desire to go lower. But really, I mean, we discussed this in our group. You get so low, it's a lot of work for not a lot of benefit at the very lowest level.
Cool. And a second question would be, what might be some other uses for the kind of information you can pick up here, especially with regards to certain identifying issues about crops or plants, etc.?
Yeah, I think we found that there is quite a lot of different use cases for irrigation data. So for example, with public policy, there's one interesting use case is identifying if certain people are doing illegal irrigation. So this high resolution makes that particular use case especially much easier to do. Yeah, from our research talking to different environmental science researchers, there was at least a dozen different use cases for this. A lot of them were related to public policy, definitely climate and weather modeling, as we talked about in the presentation, but those are a few just to mention.
To add on to that, have you guys thought about potentially considering, I'm sort of just thinking about the use case of this, the potential cost it would be, because I suspect, looking at this, you consider, what are some of the opportunity area, but given some of these regions, it could be extremely expensive. Taking into consideration climate change, do you guys have any thoughts around, how to incorporate that into the data that you're outputting?
The model will work as the training is done real time, as the user selects their region and their time frame. So the model should be robust in the future if the climate for any given area has changed.
Yeah, I wanted to let you know it's amazing that you've done so much work to get it to this point. Really appreciate the thoughtfulness and the amount of effort that went into it. My question is around the assumptions around cropland. You made a few assumptions early on around cropland. How did you arrive to those assumptions, and what do you think is going to be the consequence of those assumptions? It was like a major assumption that you made in your cropland, so I wanted to connect on that.
Yeah, so, do you want to take that, Angela, or do you want me to start?
Go ahead, Matt.
Yeah, so one of the key ones was around looking at focusing on cropland irrigation. So kind of the reason, the impetus behind that is really that research has shown that cropland irrigation accounts for 70% of freshwater usage worldwide. So that is the data that we actually have access to. So those two kind of components is the reason we focus very specifically on that area.
Yes, just to add to that, the cropland data, we identified the most accurate we can find is GFSAT 1000, NASA-funded project. And it does help us to narrow the clustering to just the cropland rather than doing it on the entire area, because if we do not remove cropland from our data, then you are facing a lot more diverse area, then it's even harder to identify irrigated land. So that's why we chose to remove the non-cropland pixel first. However, there is a limitation to that, and the assumption we made is that GFSAT 1000 is actually 100% accurate. From looking at the data, it is accurate vast majority of time. We look at a couple of data sources. They're consistent in a lot of area, but we also do observe a few observations that they are not 100% correct. So that could be a future enhancement to the project that maybe we should have built our own high resolution cropland model first. And then from there, we can dive into the problem deeper and then separate irrigation from the ring fed cropland.
Thank you for addressing that.
Thanks very much, high-res irrigation detection team. Next up, we have teacher prints. I see you have all your backgrounds coordinated. It's great. Whenever you're ready.
All right. Well, thank you for joining us today. My name is Tim Slade, and I'm honored to introduce Kim Darnell, Anna Jacobson, and Lee Moore, collectively Team Teacher Prints. Our group came together around a vision to use data science for social good, and we're immensely proud to demonstrate a product today that represents not only the knowledge we developed over the course of the program, but also the expertise, experience, and passion that we brought with us into MIDS. Most of us can think back to a teacher whose influence on our lives resonates even decades later. These memories are fundamentally about a relationship. We remember how the teacher made us feel. But while great teachers are deeply relational, their daily work is also very solitary. Once they've left their training programs, teachers rarely, if ever, have the privilege of getting feedback from fellow professionals. This solitude makes it very difficult for teachers to reflect on their practice. But reflection is the foundation of learning. So how then can teachers improve? Teacher Prints removes this barrier. By holding up a mirror to their practice, providing quantitative feedback about the verbal communication in their classroom, and offering structured guidance for their reflection, Teacher Prints supports teachers' long, iterative journey toward teaching mastery. The mission of Teacher Prints is simple: empowering teachers around the world to envision teaching excellence through accessible, affordable instructional coaching they can get anytime and anywhere. The potential market and impact for Teacher Prints is huge. Of the 40 million primary school teachers worldwide, nearly half already carry with them every day the hardware they would need to use Teacher Prints. Given a global average class size of 24 students, those millions of smartphone-enabled teachers could use our application to help improve the educational experience for almost 500 million young people around the globe, many of whom live in low-income and rural areas.
It all starts with an audio recording. For today's demo, we'll use the soundtrack from a video showing a math lesson with Miss Angela Ray, a 4th grade teacher from New York State. Here's a clip to give you a feel for Miss Ray's instructional style.
This is kind of a little shady, but it's okay, we're gonna go with it. So I have an endpoint here, and it's going like this with 2 arrows on either end. What have I just made?
A triangle.
It's certainly not a triangle.
An angle.
What is it?
An angle.
Why do you think it's an angle?
Because they're two rays together. And
That's
they're going
exactly right.
One way and the other way.
Excellent. She said it's two. Did you see how I took the 2 rays and put them together? And what did I make when I put 2 rays together?
An angle.
An angle. Can you make an angle within your group?
Now, I know that went by kind of fast, but what I hope you got out of it is that Miss Ray is a caring, high-energy teacher who gets her students up and engaged with the material, and that's great. What you might not have noticed, if you haven't spent decades doing classroom teaching like I have, is that the students spend most of the lesson taking directions and giving brief 1- or 2-word answers. Miss Ray's voice is clearly dominating the class, although it doesn't need to. This lesson is a review. I mean, it's good teaching, but with the kinds of insights provided through Teacher Prints, it could become excellent teaching. Here's how it works. Ms. Ray begins by uploading an MP3 of her teaching and using the slider bars to tell us about her goals and predictions for her talk during the class. She indicates her teacher talk goal for lessons like this one is about 50%, but she thinks today she actually talked quite a bit more. She clicks Generate Teacher Print, and our machine learning models analyze the recording to isolate 4 educationally important features of spoken lesson delivery. How much of the class involved talking, how much the teacher and the students talked respectively, how much the teacher and the students talked over each other, and how often the room was quiet. The distribution of these features for a given lesson can deeply impact students' engagement and their learning, so managing these features effectively is critical for high-quality instruction. Ms. Ray begins to examine the different features for her lesson through the speaker wheel. This shows her that she talked about 74% of the time during this 5-minute lesson, but her students only talked about 7%. This is quite different from her teacher talk goal of 50%, but that's okay. Below the speaker wheel is guided professional reflection, including expert advice and curated online resources to walk her through the critical thinking needed to take her next lesson to the next level. The ribbon menu allows Ms. Ray to take a deep dive into the components of the speaker wheel or explore her lesson a different way through the Teacher Prints speech map. Here, Ms. Ray can see her lesson statement by statement. The speech map shows the frequency and duration of student and teacher contributions to the lesson over time. The piece of the lesson that we watched was from about 250 to 285. Ms. Ray can see the dense blocks of her teacher talk in blue interspersed with bursts of the student talk in gold. Scanning the map from left to right gives her a real feel for the lesson's conversational flow. Bringing it all together is the Teacher Prints dashboard. This printable display includes every Teacher Prints metric on a single page, making it easy for Ms. Ray to compare this lesson with others and convenient for her to share the results with colleagues. Online, the dashboard is fully interactive, so if she sees something in the overview that she missed the first time through, zooming back in just takes a click. But how do the insights delivered by Teacher Prints translate into more effective teaching? Like all self-improvement, that's really up to the individual. The evidence from this teacher print is clear. Today's lesson was about 90% talk, and the vast majority of that talk was Ms. Ray's. Reducing this to her target of 50% teacher talk will take time. But Teacher Prints will help by guiding her reflection on the mismatch between her plan and her practice, and providing resources to explore how other teachers have successfully addressed similar issues. Armed with this inspiration and information, Ms. Ray can go back to her classroom and start to implement the strategies she's learned about through Teacher Prints. As time goes on, she can continue to use Teacher Prints at regular intervals to monitor and document her progress towards this current goal, as well as others she might discover along her path to teaching excellence. Although COVID-19 and the fact that it's summer kept us from test driving Teacher Prints in a classroom, we have had a wealth of teachers, educational researchers, instructional coaches, as well as fellow data scientists provide feedback on our product throughout its development. For example, one of the teachers suggested that we make some of the instructional coaching tips available through the toolbar, so folks could get a feel upfront for each of the Teacher Prints building blocks, as well as the kind of support our app can offer. The current incarnation of Teacher Prints has been characterized by testers as useful and ingenious, as well as intuitive, powerful, and important, among other nice things. We hope that you'll come visit us at teacherprints.org and let us know what you think.
So now we'll take a quick look at how Teacher Prints works under the hood. An EC2 instance hosts the Flask app serving our website and handles the pre-processing of an uploaded audio file. We have a MySQL database set up in RDS to short-circuit the inference step if we have seen this audio file before. If the file is new, we conduct our inference directly on the EC2 instance. The model outputs are then backed up to an S3 bucket for safekeeping before we serve up the results to the front end and generate our D3JS visualizations.
Our problem required developing a model that can differentiate between the voices of teachers and students. In choosing and optimizing our model, we had a few key assumptions. First, we were better off starting with a pre-trained deep learning model, if possible. We found a recent voice type classifier using a PyTorch-based framework that we called Marvin after its developer. It was built for classifying small children and adult voices trained on home-based recordings in a variety of languages. The model input is the waveform of an audio file, and the output is a multi-label classifier, providing the probability of each voice type speaking at every moment in the recording. Marvin's architecture combines a specific kind of CNN layer known as SyncNet filters with a stack of RNN layers. SyncNet encourages the first convolutional layer to discover more meaningful features by looking only at the low and high cutoff frequencies. This allows the model to converge faster and perform better than a standard CNN. Our second assumption was that it was important to ensure our model did not confuse typical classroom noises for speech. This was identified early as an issue, and so we decided to incorporate a speech activity detection model into our architecture, specifically fine-tuned to address the differences between voice, music, and other sounds. And we used this as a mask for our voice type classification results. Third, We assumed that our voice type classifier would perform better in a classroom setting if it was fine-tuned on actual classroom data. So we found a data set of kindergarten classroom recordings, which we used to fine-tune Marvin. We evaluated our model against the baseline Marvin model. Our test set was annotated by hand by our expert linguist, Kim, based on 7 New York City classroom recordings. And our new model resulted in speaker activity detection scores all comfortably above 0.9. For our voice type classification results, we had a 20% increase in precision and a 10% increase in F1 score over our baseline model. Overall, our efforts resulted primarily in uplift to precision, which was our focus, as each prediction we provided in the teacher print should accurately reflect the true speaker type. When we reflect on our modeling approach, a few key themes come to mind. Firstly, some of our modeling efforts were more rewarding than others. Specifically, most of our performance uplift came from incorporating our speech activity detection model, despite this taking the least amount of our modeling time. Second, working with audio recording labels can be messy. Our efforts to retrain Marvin on kindergarten data did not improve the model's performance as expected. We attributed this originally to how the data was annotated. As you can see in this image of human annotation, the red and blue speaker labels are right next to each other. This is because the annotators mark when a speaker started talking, but not when they stopped. As a result, the annotation ignores any silence that would have naturally occurred. We spent a lot of time trying to pre-process the data, but this didn't help. After seeing our results, we began investigating the kindergarten data more closely, and we came to realize that many of the labels themselves were poorly assigned, which explains even further why our model retrained on this data didn't improve the overall performance. Our last reflection is that while this tool could be useful for all teachers, irrespective of the age of their students, our model is only appropriate for elementary school classrooms. Alternative modeling approaches could have been used to distinguish the teacher's voice from everyone else's, such as an individual speaker identification model, but it would have resulted in trade-offs with the user experience.
Beyond the MVP, we have many ideas for additional development. These ideas fall into 3 main buckets. The first is re-annotating our training data to retrain and improve the performance of our model. The second is further model development to accomplish additional tasks such as individual speaker identification and speaker quantification. Finally, the third area for development is the product itself, including building out the mobile app and adding functionality for storing and comparing different teacher prints. We also would want to conduct more user testing, particularly in non-US classroom settings. In addition to the technical learnings that Lee touched on, we have some broader takeaways. These are closely aligned with the ethos of human-centered design, or more specifically, what we call human-centered data science. First is the importance of understanding the context. Data science has to be sensitive to its context, which includes both its domain and the culture of its users. This means that technical expertise is not enough. A strong data science team must both bring a diverse set of experiences to their work and be willing to invest a lot of thought and effort to develop an explicit understanding of their users. Next is the need for interpretability. Data science can provide powerful information, but its implementation can be intimidating and opaque. Products need to be understandable to be useful. We were constantly tempted to add complexity to our analysis and had to work really hard to keep it simple. Finally, the challenge of doing good. Data science for good can't just mean good for us. Everybody deserves good data science. Thinking about what we could accomplish beyond commerce and capitalism was hard, but ultimately we feel more important to the world. Understanding the interplay of teacher and student talk in the classroom is incredibly valuable because managing talk time well is critical to a teacher's success. Our team has combined our collective decades of experience to ensure that Teacher Prints provides users with an intuitive analysis to help them reflect on their practice and take positive steps to becoming the best teachers that they can be. We entrust teachers with our most precious resource, our children, but teachers are also the most under-resourced professionals in the world. For the tens of millions of teachers globally who lack access to effective professional development, Teacher Prints allows anyone, anytime, anywhere to envision teaching excellence.
That's the end, Drew. I just saw you drop the 2 minutes left warning.
Excellent. Thank you so much. Judges, question for Teacher Prince team.
I have so many thoughts and so many questions I want to share. First of all, what a really thoughtful presentation. I really appreciate that you put in so much thought into your audience and the impact this would have on your audience, because they're an incredibly critical one. Second, whoever did your design, like, can I hire you? Because it is just so beautifully done.
That is all Anna. Anna. She is amazing.
It is absolutely beautiful, and like, I'm actually kind of not kidding.
You know, and Raman, it's okay, because if you go to teacherprince.org, we have a shop and you can actually get swag with her designs on them. So you can take Anna's brilliant work with you.
I do want to ask a few questions about Teacher Prince itself. And you did point out that, you know, it really only works for elementary, and it's because it's sort of the voice identification. I don't necessarily see that as a weakness. I think when we're talking about this very specific use case of who's talking how much and when, one thing you might want to differentiate is, you know, this is not necessarily a useful metric for all types of education, right? And especially the higher up you go in education, frankly, the less students are often talking. So teachers are spending more time literally lecturing, and there's less of this like interactive experience. So first of all, I wouldn't necessarily think of that as a detriment, but really more of a function of, you know, how our learning education system is kind of structured. I will though point out that, you know, amount of time learning, speaking is just one thing you can do with voice prints, and I would think of other things you could do. And I'm kind of cheating here because a few years ago, I did this project through BBC's 100 Women, and we did something quite similar, but it was actually to record people's voices in meetings, and it was to identify multiple things. Ultimately, it was about how much women speak versus how much men speak, so you can do things gendered, but also in terms of like how often people are interrupted, how often people are doing the interrupting. And that's one interesting thing. I just know this from when we did our project. What you're seeing when, you know, you can't really pick up when someone's ending and someone else is talking is the way human beings talk. We just kind of like run into each other when we talk, right? Like I'm saying something, you're getting excited, you go, oh yeah, like while I'm talking, right? So that's kind of a difficulty in doing voice prints. And sometimes it's a negative thing because someone's being interrupted, and sometimes it's a positive thing. You could do things like sentiment analysis, right? Do the students sound positive when they're talking? Does the teacher sound positive? You know, going back to the gendered component, you know, we do know that in early childhood education, sometimes teachers will have an unconscious bias where they prefer boys for questions over girls, depending on the kinds of questions they're asking. So that's just a few things you might want to think about. You know, and again, like I don't really have questions for you, just like so many thoughts, given that I've done something similar, and I'm impressed at the potential for this. The other thing I will highlight, I appreciate that you spent a lot of time thinking of a singular use case and making it very, very, very good, instead of saying, let's try to bite off more than we can chew and have some sort of like a hacky presentation. So I just did want to point out that I really did like that component of it. That's just sort of sorry, that's my dog wanting to play. That's sort of the groundwork of developing a very good product. So I might suggest, you know, future roadmap, the few things I suggested, as well as just kind of give some thought of your own to other kinds of use cases for voice recognition. One thing I will highlight though, the reason we never made our tool public was concerns about privacy. You are dealing with children, things people are saying, that will probably be a blocker and a concern. I don't know if you all have thought about that at all.
Yeah, actually, under resources, we have some frequently asked questions, and one of them is it okay for me to upload a audio of my class? Is it safe? And yes, it's absolutely true that audio recordings are in the United States protected educational records, but it's also possible for parents to give permission for recordings of their children's voices to be uploaded, and parents have significantly less concern about the audio of their children's voices being uploaded than video. And since this is audio based, that addresses some of that concern. But we do encourage users to make sure that they abide by FERPA restrictions, that they check with their principal, that they make sure that they get permission. And once the data is uploaded and we convert it into our data frames that we use to generate our visualizations, we get rid of the data. So we don't even hold on to it. So we keep our data frames, but we don't keep the original recording at all. So it's not preserved. We don't save it for anything. So that information that might reveal PII about children is nowhere to be found.
Yeah, I think to expand a little bit on some of the other use cases you were talking about, Raman, we have shared this with colleagues who are teachers, colleagues who are educational researchers, and a lot of them brought up this idea of the socio-emotional component of classroom interactions, and can we look at you know, the emotional tenor of the conversation and all that kind of stuff. And the answer is yes, but as you noted, we chose to go narrow this time to just sort of do a proof of concept and then look at building things out later. One of the other things that was a priority for us and really drove a lot of what we chose to do from a design standpoint was that we wanted it to be language agnostic. And so there's a whole sort of space of questions you can begin to answer if you go with automated speech recognition that then gives you language that then you can do NLP work on and all those kinds of things. And we deliberately wanted to stay away from that because the inspiration from this, or for this, came from work that my colleagues and I have done in East Africa and Southeast Asia with minority language communities for whom there are no NLP models available. And so if we began from an assumption that we were going to go ahead and use the semantic content of language to inform our coaching, right off the bat, you know, 80% of the target population that we want to work with just doesn't have access to this anymore. And so we chose from the beginning to focus on analyzing the audio print independent of any language content in order to be able to keep the potential target audience wide.
I have a question regarding sort of just the overall how you set target. So in the example you give, let's say this person recognized that, you know, maybe 72% or 70% of his time she spent talking. How, I guess I'm trying to understand how do we know, how would they know what is actually good? If they set their target at 55%, is there actual studies that says that? I think, you know, from the example you give, it seems like the right direction, but how do we know which way is directionally more healthy for teachers to move towards?
Well, there's a substantial amount of research indicating that the more students engage verbally with material, the more it sticks, the more they're able to integrate it with other things they know. But there isn't any single percentage that's the right percentage. And for example, in the demo, we talked about a review lesson. And in review lessons, we would expect the students to have much more verbal engagement and the teacher to have much less verbal engagement. That would be different if she were giving an introductory lecture or introductory presentation where she's going to lead the conversation a lot. And the students are going to have very limited verbal involvement. So we leave this up to the individual to say, here's my goal and here's where I want to be and here's what I'm going to work towards, because I think I'm a professional and this is what I think is best in my class. And this is what I'm working towards and what my teaching colleagues have suggested is a good goal. So this is very individually driven. And there is no good, perfect, right answer. There's just the right answer for that teacher and their class.
I think one of the things, Sharon, to sort of as an example, is that it is very common in schools of education, largely in the US, not so much in the developing world, to actually video record one of your own lessons and then sit with a coach or a peer teacher and watch the video and watch your own pedagogical moves as you deliver the lesson. That is a fairly traumatic experience for teachers, at least the first time, because one of the things that comes to the fore is that they're actually often much less self-aware than they expected. And so the things that they thought they were doing, turns out they weren't doing. And you know, they thought they were being really good about giving space to their students to respond, and in fact, they were just like jumping right in, right? And so part of what this is, the ethos behind this tool is to not impose one right answer on the teachers, but it's rather to develop habits of reflection and thought so that they can become more self-aware. They can bring their perception of their actions in alignment with the perceived reality by their students, and then as a result, become more effective instructors over time.
Thank you very much, Team Teacher Prince. And that is all 8 presentations for the showcase. So we saw a group of very impressive projects tonight. So thanks everybody. Thank you to the capstone students for sharing your excellent work with everybody. And congratulations again on graduating MIDS. So the winners of the Hal Varian Capstone Award will be announced in the next few weeks. I'd like to take this opportunity to thank our judges, Deval Bhatt, Ruman Chowdhury, and Sharon Lin. And I am looking forward to discussing these projects with you all further. I also want to take the time to thank our capstone instructors, David Steyer, Joyce Shen, Alberto Todoshini, Puya Vahabi, and Fred Nugent, and all of our other MIDS faculty as well. I'd like to thank Gina Ellison and Alice Jose for Zoom support for the evening, and I want to thank everybody else who joined us tonight for the showcase. Thanks everybody, have a great night.